Beneath the slow undulation of a reef at twilight, where light falls through the water like molten glass, an octopus glides along the ocean floor. Its movement is fluid, neither swimming nor crawling, but something in between, a rippling translation of thought into motion. Every arm seems to possess an independent will, exploring crevices, tasting currents, and feeling the contours of the world with delicate precision. To watch an octopus move is to witness cognition without words, a kind of silent conversation between body and environment. This creature, often dismissed as alien, embodies one of evolution's strangest experiments. A brain split between head and limb, centralized thought and peripheral awareness, instinct and learning fused into a single flowing being. The octopus is, at its core, a paradox. It is soft, boneless, and short-lived. Yet it demonstrates problem-solving skills that rival some mammals and birds. It can unscrew jars, dismantle locks, and even recognize individual humans, showing preference or irritation toward specific divers. In captivity, they are infamous escape artists. An aquarium lid left unsecured is an open invitation. The animal will slither upward, its body compressing through impossibly small spaces, guided by the sensitive suckers that taste the world as much as they feel it. Once free, it remembers the route, a mental map of pipes, pools, and shadows, and will follow it again with astonishing accuracy. What makes this possible is not just memory, but a form of decentralized intelligence unmatched in the animal kingdom. The octopus's nervous system is not confined to its head. 2/3 of its neurons are spread throughout its 8 arms. Each arm can make decisions independently, reacting to touch, shape, and pressure faster than signals could reach the central brain. This phenomenon, known as distributed intelligence, grants the octopus a kind of bodily autonomy that blurs the line between mind and muscle. When one arm investigates a rock, it doesn't simply relay information back to the brain, it interprets and acts on it, deciding whether to explore deeper or withdraw. The result is a creature that appears to think in multiple places at once, its cognition woven through the tentacled fabric of its body. Imagine a camera drifting beside one as it moves across the sand. Each arm unfurls with surgical grace, testing textures with hundreds of suckers capable of distinguishing smooth coral from rough limestone or edible crustacean from inedible debris. These suckers contain chemoreceptors that allow the octopus to literally taste what it touches. When an arm brushes against the faint chemical signature of crab, the local neurons trigger a quick grasping reflex, long before the central brain is even aware of it. This efficiency, this distributed control, gives the octopus an almost algorithmic precision. Its body is an organic computer running dozens of sensory motor programs simultaneously, all contributing to a single emergent behavior: survival. In the evolutionary timeline, this intelligence developed along a path far removed from our own. Vertebrate brains evolved around a centralized spine, concentrating processing power in a head equipped with eyes and ears. The octopus, an invertebrate mollusk, took the opposite route. It discarded its shell millions of years ago, trading protection for adaptability. Devoid of armor, it became a shapeshifter, able to flow into cracks, mimic rocks, and vanish in plain sight. The cost was vulnerability. The reward was unparalleled flexibility. Intelligence, in the octopus's case, became its armor. Learning replaced instinct. Each individual must master the art of disguise, hunting, and escape anew, because unlike social mammals, there are no teachers. Octopus young hatch alone, left to navigate the reef with no parental guidance. Every skill, from stalking shrimp to building a den, must be learned through trial and error. This self-taught intelligence extends into remarkable tool use. In the tropical Indo-Pacific, coconut octopuses have been filmed carrying empty coconut shells across the sea floor, sometimes 1/2 in each arm, then reassembling them when danger approaches, forming an impromptu shelter. It is a behavior that demonstrates foresight. The animal collects and transports an object not for immediate use, but for a future contingency. Such anticipation of future need is exceedingly rare outside humans and higher mammals. Even more telling is that individuals refine their techniques over time, choosing shells of the right size, learning to fit them together more efficiently. The octopus does not simply react to its environment, it manipulates it, bending external elements into extensions of its will. In laboratory experiments, octopuses have shown both short-term and long-term memory. When presented with a puzzle box containing food, they learn the unlocking sequence through repetition and retain that knowledge for weeks. Their problem-solving abilities improve through practice, suggesting not just memory, but adaptive learning, an internal evaluation of success and failure. Some scientists compare their behavior to that of primates using tools or ravens solving logic puzzles. Yet the octopus achieves this without social learning, without language, and without the benefit of seeing others perform the task. It learns alone, guided by experience, and a brain architecture entirely unlike our own. Its short lifespan adds another layer of mystery. Most species live only 1 to 2 years. This means their intelligence must develop rapidly, compressed into a fleeting window of existence. Evolution has tuned them for accelerated learning, a nervous system that rewires itself constantly, neural circuits that respond to environmental feedback almost in real time. When an octopus changes color and texture to match its surroundings, it's not just camouflage, it's instantaneous environmental computation. Specialized skin cells called chromatophores expand and contract to produce hues, while papillae alter skin texture from smooth to bumpy in milliseconds. The arms feel the surface, the brain interprets the data, the skin reacts, creating a living projection of the environment itself. Its camouflage has sensory feedback loop, a biological process that behaves more like adaptive software than static disguise. This learning extends to hunting. An octopus observing a crab retreat into a burrow will test multiple strategies, probing from different angles, blocking exits with stones, or flushing the prey out with jets of water. Over time, it refines these techniques, remembering which worked best in each context. In this sense, every octopus becomes a one-animal experiment in cognition. The reef serves as its laboratory, and survival is the only measure of success. Inside the head, the brain reflects this constant need for sensory integration. Large optic lobes process visual information, while tactile and chemical data pour in from the arms. The brain's architecture emphasizes flexibility, neurons capable of forming and breaking connections rapidly, supporting short-term decision-making and long-term adaptation alike. When researchers examined octopus brains under microscopy, they found complexity rivaling that of dogs. Yet, unlike vertebrates, the octopus brain is shaped like a donut. Its esophagus passes through the center. It's a vivid symbol of how evolution sculpted intelligence through entirely different blueprints. Perhaps the most profound question is not how the octopus thinks, but what it experiences. With neurons spread through its limbs, sensations of touch, taste, and movement occur directly within the arms. Each limb might perceive the world slightly differently, an orchestra of perspectives merging into a single sense of self. Philosophers and neuroscientists alike have debated whether such a system produces a unified consciousness or a collective one. Is an octopus 8 minds cooperating or one mind distributed across 8 agents? Experiments suggest integration. The arms coordinate seamlessly when hunting or escaping. Yet the autonomy remains. Cut off one arm, and it can still respond to stimuli, curling defensively or grasping objects for minutes afterward. This autonomy also plays a role in regeneration. When an arm is lost to a predator, new tissue begins growing almost immediately. Over weeks, nerve pathways reconnect, muscle fibers reform, and sensory feedback returns. The octopus remembers how to use its new arm as if nothing happened. It does not need to relearn the movement pattern. The memory of control seems embedded in the neural circuits of the body itself. Intelligence, for the octopus, is not stored in a single location. It's distributed across flesh, nerves, and motion, a living network more resilient than centralized cognition could ever be. As night deepens over the reef, the octopus slips from its den. Its chromatophores shimmer faintly, reacting to starlight filtered through water. It moves with confidence born from memory, recalling where crustaceans hide, where predators lurk, where escape tunnels lead. Each decision, each movement, is the result of learning shaped by countless interactions. It is evolution condensed into awareness. In the silent theater of the ocean floor, This creature demonstrates that intelligence is not exclusive to those with bones, or long lives, or spoken language. It shows that cognition can evolve from entirely different materials, built from skin, muscle, and nerve. The octopus learns not by watching, but by doing. It adapts not through instruction, but through curiosity. Its world is tactile, immediate, and alive with data. To watch it work is to glimpse the mind of the sea itself, curious, adaptable, and endlessly inventive. And when its arms curl gently around a shell, a rock, or the hand of another living thing, you are not merely seeing touch. You are witnessing thought in motion. The ocean, through the octopus, is thinking with its hands. At dawn, the sea is glass. Pale light filters through the surface, refracting into shifting patterns that paint the sandy shallows below. A faint chorus of clicks, whistles, and pulsed calls breaks the silence, an invisible language rippling through the water. The source soon appears, a pod of bottlenose dolphins, slicing through the surf in perfect coordination. They move as if choreographed, each member anticipating the next's motion with a precision that seems telepathic. But this is not magic. This is culture, learned behavior refined through generations, shared knowledge passed from mother to calf, and the fluid intelligence of one of the ocean's most sophisticated societies. Everywhere dolphins live, the water becomes an arena of teaching and imitation. Unlike fish or turtles, which rely mostly on instinct, dolphin survival depends on learning. A young calf's first months are spent almost entirely in its mother's slipstream, where it mimics her every movement, how she surfaces to breathe, how she dives, how she adjusts her sonar clicks to probe the seabed. Each behavior is copied, practiced, and refined through observation. This is not mindless mimicry, it's structured apprenticeship. The calf watches, tries, fails, and adjusts. A dolphin's education is a process of constant calibration, guided by patience and repetition. Nowhere is this more vividly displayed than in the shallow bays of Western Australia, particularly Shark Bay, a world-renowned hotspot of dolphin intelligence. Here, females have been observed performing a behavior so specialized it reshaped how scientists understand animal learning: sponge foraging. The dolphin selects a marine sponge, tears it free from the seafloor, and wears it over her beak like a glove. With this makeshift tool, she probes the rough, abrasive seabed in search of buried fish. The sponge protects her rostrum from stings, scrapes, and hidden spines. What's remarkable is not just the innovation, but the inheritance. Calves learn this behavior directly from their mothers, never from males, and rarely from unrelated dolphins. The practice spreads matrilineally, forming what can only be described as a cultural tradition. Some lineages are spongers, others are not. It's a behavioral lineage that parallels how humans inherit crafts or dialects. This capacity for cultural learning requires more than intelligence. It demands memory, communication, and a shared social framework. Dolphins maintain relationships through vocal signatures unique to each individual. These are known as signature whistles, acoustic names that identify one dolphin to another. When separated, a dolphin will broadcast its whistle repeatedly, waiting for a response in kind. Experiments have shown that individuals can remember the signature whistles of companions even after 2 decades apart. Such memory spans are astonishing for a non-human animal, rivaling the long-term recognition abilities of elephants and great apes. In the open ocean, where groups fission and fuse frequently, this auditory naming system allows dolphins to maintain complex social networks across miles of shifting territory. Communication among dolphins is layered, blending sonar, body posture, and acoustic nuance. Echolocation, one of their most remarkable sensory systems, serves not only to locate prey but also to transmit information. Each dolphin emits bursts of high-frequency clicks that reflect off nearby objects, forming an acoustic image processed in the brain's auditory cortex. This sonar is so precise it can detect a fish buried beneath sand or the density of another dolphin's internal organs. But beyond foraging, dolphins use these echoes socially, scanning each other's bodies as if reading a 3-dimensional story. It's not unreasonable to suggest they can see with sound the way we see with light, perceiving both external form and inner structure. Their brains reflect this complexity. Relative to body size, dolphin encephalization rivals that of great apes. The neocortex, responsible for reasoning and planning, is highly folded, increasing surface area for neural processing. This architecture supports behaviors like cooperation, empathy, and imitation. Dolphins not only understand the intentions of others, they anticipate them. In cooperative hunts, each individual adjusts position based on the movements of its peers. No single dolphin commands, yet the group acts as one organism. One of the most striking examples of coordinated intelligence is bubble net feeding, a behavior famously practiced by humpback whales, but also observed among dolphins. When a pod encounters a dense school of fish, several individuals dive beneath it, circling in tight formation while releasing streams of air from their blowholes. These bubbles rise, forming a shifting wall that traps the fish inside a cylindrical cage. Other dolphins drive the prey upward while the rest surge through the center, mouths open. The teamwork required is extraordinary. Timing, positioning, and communication must be flawless. Calves often watch from the periphery, mimicking the motions in miniature until they're ready to join. Play in this context is not frivolous, it's training. Through mock hunts, juveniles rehearse the synchronization, reflexes, and social awareness needed for real success. Play is, in fact, central to dolphin learning. They chase each other through surf waves, toss seaweed back and forth, and sometimes interact with other species, including humans, purely for the sake of interaction. These games serve developmental purposes, improving agility, coordination, and communication. In groups of young males, play can also shape dominance hierarchies, forming bonds that later translate into coordinated alliances for mating access. Some dolphins engage in imitation games, copying each other's actions or vocalizations in apparent amusement. Such imitation reveals self-awareness, a recognition of one's actions in relation to another's. It's a cognitive leap shared by only a handful of animals, including humans, elephants, apes, and certain corvids. As we descend deeper into the dolphin's cognitive world, the boundaries between instinct and culture blur. For instance, when a dolphin learns a new trick in captivity, like tail walking across the surface, it can spontaneously spread that behavior to wild populations. In one documented case, a released dolphin taught her podmates to perform the motion purely through observation, decades after her human training ended. This transmission of learned, non-instinctual behavior between individuals is a hallmark of cultural evolution. It suggests that dolphins, like humans, live within societies shaped not only by genetics, but also by knowledge. In the wild, the importance of maternal mentorship cannot be overstated. A calf remains by its mother's side for several years, nursing for up to 2.5 years and learning through shadowing. Mothers enforce lessons through gentle correction, nudging calves away from danger, steering them toward fish schools, or calling them back with low-frequency whistles. The calf's survival depends as much on what it learns as on its physical strength. Every skill, from recognizing the signature whistles of allies to evading sharks, must be practiced through guided experience. Even their relationships with predators are learned. Young dolphins often approach sharks cautiously under adult supervision, mimicking the defensive formations used by the group. When threatened, dolphins form tight circles, facing outward with their beaks ready to ram. They know precisely how to strike the gills or underbelly, the most vulnerable points. Calves watch these confrontations carefully, internalizing the choreography. Over time, these lessons become reflexive, encoded not through instinct but through social education. Their intelligence extends into emotional realms too. Dolphins exhibit empathy and altruism across species boundaries. They've been documented supporting injured companions to the surface, assisting stranded whales, and even defending humans from sharks. These actions appear spontaneous without obvious self-benefit. While it's tempting to romanticize such behavior, it aligns with neurological evidence. The dolphin limbic system, the seat of emotion, is proportionally larger than that of many primates. Their capacity for social bonding and emotional response likely evolved to maintain cohesion within dynamic, fluid groups. Yet intelligence comes at an ecological price. Large brains require immense energy, and dolphins meet that cost through cooperative hunting and high-calorie prey. Their societies evolved in environments rich with opportunity, coastal shallows teeming with fish, squid, and crustaceans. In leaner seas, such social intelligence might have been unsustainable. Thus, dolphin culture is not just a product of mind, but of environment, a convergence of cognitive potential and ecological abundance. When viewed from above, a dolphin pod cutting through calm seas resembles a living neural network. Each body is a node, connected through waves of sound, motion, and intent. Knowledge flows between them like electrical impulses, carried not through wires but through shared experience. Over generations, this transmission builds a legacy, behaviors that persist long after individuals die. The ocean becomes their classroom, the current their blackboard, every calf another student of the tide. In the final light of day, as the sun drops toward the horizon and turns the water gold, a mother and calf surface together. The calf mimics her breath, the arch of her back, the rhythm of her dive. Below them, others weave through the dimming blue, clicking softly in conversation. They are not just surviving, they are learning, teaching, remembering. Theirs is a society built on connection, a lineage not of blood alone but of knowledge. In these teachers of the tide, the ocean reveals its most enduring truth. Intelligence is not confined to the land. It flows with the current, carried in echoes and play, passed from mother to child beneath the waves. It is education without classrooms, mentorship without words, a language written in sound and motion. The dolphin's legacy is proof that the sea itself can think, and that its lessons endure in the minds of those who listen. Beneath the turquoise shimmer of a shallow reef, the cuttlefish waits. Suspended just above a mosaic of coral and sand, it is almost invisible, its skin a living replica of its surroundings. The boundary between flesh and rock dissolves, the edges of its body dissolving into light and shadow, as if it were a trick of vision rather than an animal at all. But within that stillness lies a computation more complex than any performed by machines, a biological algorithm that processes color, texture, movement, and threat in fractions of a second. This is not simple camouflage. It is decision-making in motion, a continuous flow of perception and adaptation that allows the cuttlefish to survive in an ocean full of eyes sharper than its own. A cuttlefish does not see the world as humans do. Its eyes are shaped like the letter W, capable of detecting polarized light, subtle contrasts, and shifts in brightness that most creatures miss entirely. Yet paradoxically, it is colorblind. The cuttlefish cannot distinguish red from blue or green from yellow. Instead, it reads the patterns of light and shadow, constructing a mental map of contrast and depth. Its camouflage is not a reproduction of color, but an illusion of it, an interpretation based on the physics of reflection. Each adjustment it makes is a hypothesis about how predators might see it. This is the heart of its intelligence, not copying the world directly, but predicting how others perceive it. Embedded within its skin are millions of chromatophores, tiny pigment sacs that expand or contract under muscular control. When expanded, they reveal vivid pigments of yellow, red, and brown. When compressed, the skin turns pale or reflective. Beneath them lie iridophores and leucophores, structures that manipulate light through diffraction and scattering, creating iridescent blues and whites. Together, these layers function as a dynamic display screen, capable of producing infinite combinations of texture and hue. The cuttlefish does not simply change color. It calculates which pattern best neutralizes its visibility, given the ambient light, viewing angle, and background composition. It's a real-time solution to a survival equation. When a predator approaches, a barracuda gliding through the coral, or a reef shark passing in the distance, the cuttlefish's body becomes a battlefield of decisions. Its eyes track the predator's speed and direction, while its mantle muscles ripple with subtle waves. The neural circuits behind this reaction are astonishingly efficient. The cuttlefish brain, though smaller than a walnut, contains one of the highest neuron counts relative to body size in any invertebrate. These neurons are wired for pattern recognition and rapid feedback. The brain gathers data through the eyes, interprets the background geometry, and instructs each patch of skin to respond accordingly. It is, in effect, a biological computer, a network that runs continuously, calculating camouflage in real time. Yet camouflage is only part of its cognitive repertoire. Cuttlefish also demonstrate behaviors that suggest planning, learning, and even self-control. In laboratory settings, they have been tested in versions of the marshmallow test, the famous experiment designed to measure delayed gratification in children. When presented with a small shrimp immediately or a larger one after waiting, cuttlefish learn to delay their response, controlling their impulses to gain a better reward later. This ability implies foresight and inhibition, traits once considered uniquely human or at least confined to mammals and birds. For a creature that lives barely 2 years, such cognitive flexibility is extraordinary. It reveals how intelligence can evolve not for social interaction, but for survival in a world of perpetual uncertainty. The environment demands it. Life on a coral reef is a contest of perception. Every animal here, from predatory grouper to ambush octopus, relies on sight to hunt or hide. The cuttlefish occupies both roles. It must be invisible to live and visible to hunt. When stalking prey such as shrimp or small fish, it uses its skin as an instrument of deception. Its chromatophores flicker in subtle waves called passing clouds, mimicking the movement of light filtered through water. These slow, rolling pulses distract the prey's attention, making the cuttlefish appear like a drifting patch of sunlight rather than a living threat. The closer it moves, the more mesmerizing the pattern becomes. Then, in a sudden collapse of stillness, its 2 feeding tentacles shoot forward from beneath its arms, lightning fast and precise. The prey disappears, swallowed before it can register the attack. But this hunter is also a learner. When it fails to capture prey, the cuttlefish adjusts its tactics, modifying the rhythm of its approach, the intensity of its color display, or the angle of its strike. Repeated exposure refines its performance, a feedback loop of action and correction not unlike machine learning algorithms. Scientists studying these behaviors have described them as evidence of episodic-like memory, the ability to recall not just what happened, but the context in which it occurred. Such memory allows the cuttlefish to adapt strategies based on previous outcomes. If a particular pattern alerted a fish before, it will not use it again in the same lighting conditions. Its mind updates its model of the world, one experience at a time. The reef itself shapes these algorithms. In open sand, the cuttlefish favors mottled patterns that break up its silhouette. Among coral branches, it shifts to complex, high-contrast designs. Even the direction of sunlight influences its calculations. When the light comes from above, it darkens the top of its body to cast natural shadows. When the light is diffused or angled, it adjusts reflectivity instead, reducing contrast that could give away its position. These decisions are instantaneous, yet grounded in physical laws of optics. The cuttlefish, in effect, performs field physics with its skin, calculating how photons behave and sculpting its appearance accordingly. Its intelligence does not stop at vision. Cuttlefish possess an acute sense of proprioception, the awareness of their body's position and movement in space. This is critical for their unique mode of locomotion. They propel themselves using a fin that ripples around their mantle like a ribbon, granting precise control over buoyancy and direction. For sudden bursts of speed, they expel jets of water from their siphon, a built-in propulsion system. These 2 methods are coordinated seamlessly: glide and burst, hover and shoot, allowing them to navigate reefs with the finesse of a drone. Every motion is optimized for minimal disturbance. Even their shadows are managed carefully, as predators below often hunt by silhouette. Their adaptability also manifests in social and reproductive behavior. During mating season, males display rapidly shifting color bands to signal dominance or courtship. Rival males engage in silent color duels, their bodies flashing in alternating stripes that convey aggression without physical conflict. Meanwhile, smaller males employ deception. They imitate the mottled patterns of females to sneak past dominant rivals and mate unnoticed. Once the act is complete, the mimic restores his true colors and slips away, a masterclass in behavioral disguise. This dual use of camouflage, both defensive and strategic, underscores how deeply the ability to simulate lies within cuttlefish intelligence. Yet for all its complexity, the cuttlefish is bound by the brevity of its life. Its existence is a race between learning and mortality. As it nears the end of its short lifespan, often less than 2 years, its neural circuits begin to degrade. Vision weakens, skin responses slow, and memory fragments. In its final days, it drifts more openly, less cautious of predators. For a moment, the ocean reclaims its secrets. The algorithms go quiet. But before that end, each cuttlefish has contributed something intangible to evolution's archive, a blueprint of distributed intelligence refined not by longevity, but by necessity. Perhaps what makes this animal so fascinating is how its body bridges biology and computation. When engineers design adaptive systems, robots that learn from experience or camouflage that changes with light, they look to cephalopods like the cuttlefish.
Its neural circuits inspire artificial networks. Its skin has informed new materials that shift color in response to electricity.
But even these human imitations cannot capture the sheer elegance of how seamlessly brain and body work together in nature. The cuttlefish does not separate perception from response, input from output. To it, seeing is acting. Its skin and mind are part of the same living process. If the octopus represents individual curiosity and the dolphin embodies social learning, then the cuttlefish is the ocean's mathematician, a creature whose very existence depends on processing the world as data. It reads light, geometry, and probability and turns them into survival. When we watch it vanish against coral or shimmer like sunlight on sand, we are not seeing instinct at work, but a living equation unfolding in real time. And so, in the quiet blue where predator and prey are locked in perpetual calculation, the cuttlefish glides like a thought made flesh, a being that doesn't just react to its environment but reasons through it. In this soft-bodied creature, evolution built not armor nor claws, but code. The sea is still when the hunters arrive. The horizon is grey with fog, the kind that muffles the sound of waves and makes the ocean feel endless. Then, out of the mist, a ripple becomes a shape, and the shape becomes a fin. Tall, black, and unwavering. It cuts the water like a blade. More follow, moving in synchrony, silent but purposeful. They are orcas, apex predators of the sea, yet also among the most socially complex beings on Earth. Each fin represents not just an individual, but a lineage, a dialect, a culture. To watch them hunt is to witness the passing of knowledge older than memory itself. Unlike most marine predators, orcas do not share a single hunting strategy or diet. Their behaviors vary drastically from region to region, shaped by geography, prey availability, and centuries of learned adaptation. In the cold fjords of Norway, pods choreograph carousel hunts, herding schools of herring into tight spheres. In the Pacific Northwest, they communicate in distinct vocal dialects that outsiders cannot decipher. Along the coasts of Patagonia, they perform one of the most dangerous maneuvers in the animal kingdom, deliberately beaching themselves to snatch seals from the sand. These are not random tactics born of instinct. They are traditions, refined, taught, and inherited across generations. To understand orca intelligence, one must first understand their societies. Each pod functions as a matrilineal unit, led by an elder female who carries not only authority, but ancestral memory. Her knowledge spans migration routes, feeding grounds, and behavioral codes. Calves stay with their mothers for life, learning every nuance of hunting, navigation, and communication by observation. The young do not merely imitate, they apprentice, guided through experience by elders who correct and encourage. This continuity of learning, transmission of knowledge not genetically encoded but socially inherited, is what scientists now recognize as culture. When viewed underwater, their coordination borders on the uncanny. Each orca's echolocation clicks form part of a communal soundscape, a three-dimensional network of data shared among the pod. Using sonar, they build acoustic maps of their surroundings, detecting fish schools, tracking ice ridges, and even identifying individual prey by size and movement. Communication overlays this sonar layer like a second channel, composed of pulsed calls and whistles that carry identity and intention. Each pod possesses its own repertoire of calls, a dialect that marks belonging. Two neighboring pods may share the same waters, yet remain acoustically distinct, like tribes speaking related but separate languages. Calves learn these calls the same way human children acquire speech, through repetition, reinforcement, and context. Consider the orcas of Patagonia. Along the Valdez Peninsula, a small population has developed the art of intentional stranding, a hunting technique so perilous it defies instinct. The pod patrols the shoreline at high tide, scanning for sea lion pups playing near the surf. When the moment is right, a female accelerates toward shore, riding a wave that lifts her onto the sand. In a spray of foam, she lunges, seizes her prey, and then writhes her massive body back toward the sea before the receding water traps her. Calves watch from the shallows, mimicking the approach in safer conditions until, after months of practice, they attempt their own strandings. Failure can mean death, but success ensures survival and the perpetuation of the skill. This behavior, seen in no other population, has persisted for decades, passed down like an ancestral craft. Far to the north, in the icy fjords of Norway, a different tradition reigns. Each winter, vast schools of herring migrate into coastal inlets, and the orcas follow. Here, the hunt is collective choreography. Several individuals dive beneath the school, releasing streams of bubbles that corral the fish into dense, swirling balls. Others circle the perimeter, flashing their white bellies to reflect light and confuse the prey. Then, in perfect timing, one orca smacks the water with its tail, a single devastating strike that stuns dozens of herring at once. The group takes turns feeding, returning for more only after the school begins to scatter. The precision of this behavior suggests rehearsal, not impulse. Younger members participate cautiously at first, then assume active roles once they've mastered the rhythm. The efficiency is unmatched, thousands of calories secured with minimal effort, achieved through coordination refined by collective intelligence. The key to understanding orcas lies in their flexibility. Each population has evolved behavioral specializations so distinct that biologists now classify them as ecotypes. In the Pacific, resident orcas feed exclusively on salmon, while transients, also called Biggs orcas, hunt marine mammals such as seals, sea lions, and porpoises. Even when these groups overlap in range, they do not mix. Their call repertoires are incompatible, their social structures divergent, and their diets so specialized that a resident orca will ignore a seal swimming directly past its mouth. Culture, more than biology, defines their identity. Their cooperative intelligence rivals that of wolves or chimpanzees, but with an added dimension: communication through sound that travels for miles underwater. When hunting seals, transient orcas fall silent, relying solely on stealth and vision to avoid alerting their prey. When targeting fish, residents are noisy, their clicks and calls echoing through the water like a bustling marketplace. This ability to modulate communication depending on context, switching between silence and chorus, demonstrates cognitive control over behavior. The orcas are not reacting blindly. They are making strategic decisions based on understanding how their actions alter the environment. In New Zealand's shallow bays, orcas engage in stingray hunts that reveal another layer of learning. Rays lie buried under sand, their venomous barbs formidable defenses. Yet orcas approach with practiced precision. One uses a burst of sonar to locate the ray, while another flips it over with a sudden flick of its tail, exposing the vulnerable underside. Working together, they immobilize the prey, sometimes carrying it to the surface for younger members to examine and taste. In these moments, knowledge is not just transmitted, it's demonstrated. Each calf watches the sequence, internalizing the steps that will one day keep it alive. What's striking is how this learned intelligence connects directly to memory. Orcas live long lives, often exceeding 70 years in females, and this longevity provides the time necessary for culture to accumulate. The matriarch's experience becomes a living library. During years when prey is scarce or sea ice shifts unpredictably, her memory of alternative feeding grounds can mean the difference between starvation and survival. Studies have shown that pods led by older females have higher survival rates, particularly in harsh conditions. Knowledge, not dominance, determines leadership. This intergenerational continuity is reinforced by emotional bonds. Orcas display strong affiliative behaviors, touching, rubbing, and vocalizing to maintain connection. They grieve for lost pod members, sometimes carrying dead calves for days before releasing them. Such behavior indicates an awareness of self and others, a social cognition rarely seen outside great apes and elephants. The same intelligence that crafts their hunting strategies also shapes their empathy and loyalty. To them, the pod is not merely a group, it is identity itself. From an ecological perspective, these cultures have sculpted entire marine systems. In regions where orcas specialize in hunting marine mammals, seal and sea lion populations remain in check, indirectly influencing fish stocks and kelp growth. Where they target fish instead, their feeding patterns drive prey migrations, redistributing nutrients through discarded remains. Even their hunting noise can affect ecosystem behavior, as prey species adapt to avoid orca vocal frequencies. In this sense, orcas are not just apex predators, they are environmental engineers, their behavior rippling through the food web in complex and far-reaching ways. And yet, their cultures are fragile. Modern threats, boat noise, chemical pollution, and dwindling fish stocks disrupt the very foundation of their learning. Underwater noise masks communication, making it harder for pods to coordinate or teach calves. Declining salmon runs in the Pacific Northwest have left resident populations starving, forcing younger orcas to adapt or perish. These pressures test the resilience of learned traditions built over generations. Whether orcas can rewrite their cultural codes fast enough remains an open question, one that may determine their future survival. As the day fades and the pod surfaces together, the air fills with the sound of synchronized breaths. A chorus of misty exhalations breaks the stillness, followed by a collective dive. Beneath the waves, their white patches flicker in the dim light, vanishing and reappearing like signals in a coded language. Somewhere in the deep, the matriarch leads, her calls echoing through the water, guiding her descendants toward familiar hunting grounds. In her memory lies the story of every chase, every triumph, every survival. To witness them is to glimpse the ocean's living intelligence, one that learns, remembers, and teaches across generations. The orca's legacy is not written in bone or DNA, but in sound, motion, and shared experience. These are the cultures of the hunt, passed through the currents of time, as alive and evolving as the sea itself. The sea is calm and endless, a blue plain stretching to the horizon. Far below, sunlight fades into gradients of cobalt, then into black. In that vast, unbounded world drifts one of the planet's greatest teachers, the humpback whale. Its presence feels geological, like a moving continent of flesh and sound. At nearly 40 tons, it carries the weight of generations, the memory of oceans past. But what truly defines this giant is not its size, it is its voice. A voice that travels thousands of miles through water, reshaping itself along the way. The humpback song is one of nature's most remarkable forms of cultural transmission, a melody that evolves, spreads, and mutates like language itself. To the human ear, the whale's song sounds haunting and otherworldly, a blend of moans, clicks, and rhythmic cries rising and falling through layers of the sea. But to another humpback, it is a code. Each song is composed of repeating phrases and structures, organized with the precision of music. Yet unlike the fixed calls of most animals, humpback songs change over time. They evolve, sometimes subtly, sometimes drastically, as new motifs emerge and old ones fade. Scientists have tracked this evolution across entire ocean basins. A new theme originating in the Western Pacific can migrate eastward, spreading from one population to the next, until whales thousands of miles apart are singing the same tune. Then, almost as suddenly, a new song appears, and the cycle begins again. This is not genetic adaptation, it is cultural evolution, passed through learning and imitation rather than inheritance. These songs serve multiple functions. Males sing during the breeding season, often while suspended vertically in the water, heads down, mouths slightly open, projecting their calls across the deep. The purpose seems to be both courtship and competition, a way to attract females while signaling prowess to rival males. Yet the complexity of the music suggests something deeper. Each phrase is performed with subtle variation, as if each singer interprets rather than recites. Over the years, scientists have observed waves of musical change cascading through populations in what they call song revolutions. Every few seasons, a completely new composition replaces the old, like an ocean-wide remix spreading from one region to another. The process mirrors human musical trends. A hit melody catches on, sweeps through the population, and is eventually replaced by the next cultural innovation. But how does such information travel across such immense distances? The answer lies in migration. Humpbacks are among the most accomplished travelers in the animal kingdom, undertaking annual journeys of up to 10,000 kilometers between feeding and breeding grounds. Their routes act as knowledge highways, connecting otherwise isolated populations. During migration, whales from different regions briefly overlap in shared waters, creating windows for cultural exchange. In these intersections, off the coasts of Polynesia, the Coral Sea, or the Central Pacific, songs are heard, copied, and carried onward. The pattern is distinctly eastward. The cultural wave begins near Australia and moves across the ocean, population by population, all the way to South America. In the span of just a few years, a melody born in one pod can reach whales an entire ocean away. No other non-human species exhibits this scale of cultural diffusion. The humpback's mastery of sound is not limited to communication, it is integral to their hunting strategies as well. In the cold, nutrient-rich waters of Alaska, humpbacks form cooperative feeding groups that execute one of the most extraordinary tactics in the marine world, the bubble net hunt. A small group locates a school of herring near the surface, then dives below in synchronized formation. One whale begins releasing a spiral of air bubbles, encircling the prey in a shimmering cage of oxygen. The other whales join in, their calls rising through the water, low-frequency feeding cries that herd the fish into the center. The bubbles act as both barrier and signal. The fish, disoriented by the vibration and light, compress into a tight mass. Then, in perfect unison, the whales surge upward through the net, mouths agape, engulfing thousands of fish in a single coordinated strike. What makes this behavior remarkable is its learned nature. Not all humpbacks know how to perform bubble net feeding. It is not an instinctive behavior like breaching or tail slapping. Juveniles observe and practice under the guidance of experienced adults, often taking years to master the timing and coordination required. Each group develops its own style. Some form tight spirals, others produce multiple nets in succession. The sound signatures used to signal the attack also vary, functioning like dialects. These differences persist across generations, suggesting localized traditions. In essence, humpbacks possess both a musical and a behavioral culture, each transmitted socially and refined collectively. The ocean's acoustic environment makes this possible. Water transmits sound nearly 5 times faster than air, allowing the whale's songs to travel across entire ecosystems. Low-frequency notes can carry for hundreds of kilometers, reverberating through thermal layers that act like sound channels. These natural corridors, known as the SOFAR channel, allow humpback songs to propagate efficiently, connecting distant pods. It is a system that predates our own telecommunication networks by millions of years. And like any communication system, it is sensitive to interference. The increasing roar of ship engines, sonar, and industrial noise now masks these frequencies, fragmenting the whale's sonic world. In some regions, males have been observed simplifying their songs, likely as an adaptation to acoustic pollution, a sobering reminder of how human noise reshapes even the ancient languages of the sea. When not feeding or breeding, humpbacks inhabit a world defined by sound and memory. Their migrations follow ancient routes, guided not by sight but by internal navigation systems tuned to the Earth's magnetic field, the position of the sun, and possibly even infrasound cues generated by the planet itself. Mothers teach calves these routes through experience, swimming side by side for months as they cross open ocean. The calves learn not only geography but rhythm, the timing of feeding seasons, the patterns of temperature and light, the feel of the current. This is knowledge passed through the senses, woven into instinct through repetition. The result is a collective memory that stretches across generations, a migratory tradition older than civilization. Perhaps the most astonishing revelation about humpbacks is their capacity for innovation and improvisation. While their songs evolve through imitation, individuals often introduce new elements, brief variations, altered sequences, or rhythmic changes that catch on among peers. Over time, these additions accumulate, transforming the composition entirely. It is a living form of creativity, one that balances conformity with exploration. Such cultural flexibility reflects a deep cognitive ability, the awareness of others' behavior and the capacity to modify one's own in response. This interplay between individuality and imitation lies at the heart of humpback culture, sustaining its continual evolution. Even their acrobatics carry meaning beyond spectacle. Breaching, in which a whale propels its entire body out of the water, is thought to serve multiple functions: communication across distance, parasite removal, and social signaling. The thunderous crash of re-entry can be heard for miles underwater, a physical punctuation mark in the language of the deep. Calves learn to breach by trial and error, often launching themselves repeatedly in playful sequences, guided by maternal encouragement. Through these physical displays, they develop the strength and coordination needed for migration, as well as the social bonds that define their pods. In the grander scheme, humpbacks function as oceanic architects. Their feeding behavior redistributes nutrients vertically through the water column. When they dive deep to feed and return to the surface to breathe, they release plumes of fecal matter rich in iron and nitrogen. This whale pump fertilizes surface waters, fueling phytoplankton growth, the microscopic base of the marine food web. In this way, the songs and movements of humpbacks contribute to the health of entire ecosystems. The ocean's productivity literally resonates with their presence. As evening descends over tropical waters, a single male begins to sing. His song spirals through the dark like a pulse, complex yet deliberate, carrying across miles of quiet sea. Others hear it and join, overlapping harmonies weaving into a rolling symphony of sound. Somewhere in the deep, calves listen, absorbing patterns they will one day reproduce with their own variations. The ocean becomes a classroom and sound becomes heritage. Each note holds the memory of migration, the rhythm of feeding, and the instinct to teach through imitation. Through the humpback whale, the ocean reveals itself not just as a habitat, but as a medium of knowledge, a vast blue archive where learning and tradition echo through time. Their songs are more than courtship calls. They are records of adaptation, creativity, and communication on a planetary scale. They remind us that intelligence does not always wear a face or build a tool. Sometimes it drifts in the depths, carried on sound waves, teaching across generations in the oldest classroom on Earth, the open ocean. The morning fog still clings to the Pacific coastline, a silver veil stretched over the kelp forests swaying just beneath the surface. From above, the ocean looks calm, even tender, but under that shifting mirror is a world of motion, a dense forest of golden-brown fronds rising toward the light, tangled in perpetual sway. Among the broad kelp leaves, small bubbles cling to the surface like glass beads, and the faint sound of waves echoes as a rhythmic hush. Here, on this cold and nutrient-rich edge of the world, a teacher floats on her back, and beside her, a pupil. A sea otter pup, wrapped in the soft insulation of its own buoyant fur, stares upward toward the grey sky while its mother digs beneath the kelp canopy. For this species, survival is not inherited through instinct alone. It must be taught, one shell and one stone at a time. The sea otter, though small among marine mammals, is an evolutionary anomaly, a creature that returned to the water but never fully gave up the habits of land. Unlike whales or seals, it carries no insulating layer of blubber. Instead, it relies on the densest fur in the animal kingdom, up to 1 million hairs per square inch, to trap a layer of air against its skin. This fur must be groomed constantly, cleaned and fluffed to maintain buoyancy and warmth. Every few hours, a sea otter will twist and roll, combing through its coat with nimble paws to keep that insulating barrier intact. It is an ongoing ritual of maintenance, a survival mechanism as much as a sign of comfort. But fur alone cannot sustain life in the cold Pacific. The otter burns energy at a relentless pace, its metabolism running up to 3 times faster than a human's. To fuel this furnace, it must consume 1/4 of its body weight in food each day. And that necessity, feeding with precision, speed, and ingenuity, is what makes the otter both student and teacher in one of the ocean's most extraordinary classrooms. Below, in the dim corridors of kelp, the mother works methodically. With quick dives, she scours the rocky seabed, feeling along crevices with her sensitive forepaws. Each dive lasts barely a minute, but her movements are practiced and exact. When she surfaces, her chest becomes a floating workbench. In one paw she holds a sea urchin, in the other a stone smooth enough to serve as an anvil. She flips onto her back and begins to hammer, sharp, deliberate strikes that echo faintly across the bay. The urchin cracks open, spilling a burst of orange gonads, rich with fat and protein. She eats quickly, then repeats the motion for her pup to see. The pup watches with wide eyes, occasionally reaching toward the stone, imitating the gesture clumsily. It is an apprenticeship that may last months. Each repetition imprints a skill that will one day determine whether this young otter thrives or starves. This use of tools, one of the few documented among non-primate mammals, is no coincidence of cleverness. It is a learned tradition, passed matrilineally through generations. Different otter populations favor different methods and preferred tools. In some regions, individuals specialize in cracking open mussels. In others, they focus on snails or clams. Some favor chest anvils, balancing the prey on their ribcage while striking it. Others wedge stones against the seabed for stability. A few individuals even keep favorite stones tucked under their forearm flaps, small pouches of loose skin used to carry both tools and food between dives. This pocket stone behavior demonstrates foresight and planning. The otter carries not just what it needs now, but what it expects to use later. The transmission of these habits forms what researchers call cultural lineages. An otter's technique reflects its ancestry more than its geography. Mothers teach pups by demonstration, not instruction, repetition through example until imitation becomes mastery. In the wild, observers have noted mothers placing shells in their pups' paws, guiding the motion of cracking and even withholding food until a technique improves. It's a subtle but powerful feedback loop, one that builds problem-solving through practice. The sea otter's intelligence, while less overt than that of dolphins or primates, lies in its adaptability and precision, mental traits shaped by a life of constant manual engagement. Above the kelp canopy, these lessons unfold in floating nurseries. Mothers anchor themselves by wrapping strands of kelp around their bodies like seatbelts, forming makeshift rafts that drift with the tide. Here pups stay afloat while their mothers dive for food. These kelp cradles serve as both playpens and classrooms. The pups, buoyant and still too fluffy to dive, practice grasping kelp, manipulating stones and mouthing shells. The kelp forests provide more than just security. They are the ecological backbone of the otter's world. Without them, there is no refuge from the currents, no nursery for fish or crustaceans, no structure for an entire web of marine life that depends on stability in an ever-moving sea. Ironically, the otters are both guardians and beneficiaries of these forests. Their diet, centered around sea urchins, keeps the urchin population in check. Left unchecked, urchins graze voraciously on kelp holdfasts, the root-like anchors that tether the forest to the rocky substrate. When sea otters were hunted nearly to extinction during the fur trade of the 19th century, vast regions of kelp forest collapsed into so-called urchin barrens, underwater deserts stripped bare by unchecked grazing. The reintroduction of otters has reversed this process in many areas, restoring balance to ecosystems that depend on kelp as primary habitat. Every cracked shell, every stone strike, ripples outward through the environment, shaping the structure of entire coastlines. In this sense, each lesson passed from mother to pup sustains not just a lineage of otters, but a community of species bound by interdependence. Their ecological role reveals an elegant example of trophic cascade, how the behavior of a single predator can influence the abundance of species several levels below it. By preying on urchins, otters protect kelp, which in turn shelters fish, absorbs carbon, and slows coastal erosion. The effect is measurable even in the chemistry of the ocean. Kelp forests capture vast amounts of carbon dioxide, functioning as underwater carbon sinks. When otters thrive, kelp expands. When otters vanish, carbon absorption declines. This cascading relationship shows how intelligence, behavior, and environment intertwine, how a simple act of using a stone can alter the planet's atmospheric balance. Still, the life of a sea otter remains perilous. Without blubber, they are vulnerable to temperature drops and dependent on near-constant foraging. They must navigate a landscape filled with predators, sharks, killer whales, and sometimes eagles that seize young pups. Human threats linger too. Oil spills mat their fur, stripping away insulation, fishing nets entangle them, and coastal pollution seeps into their prey. Yet their adaptability continues to astonish. In urbanized coastlines of California, some otters have learned to forage near harbors, using man-made structures as analogues to natural reefs. Their problem-solving extends beyond tradition. It reflects an intelligence capable of reinterpreting new environments. The relationship between otters and their tools also challenges the traditional boundaries of animal intelligence. Tool use was once considered a defining feature of human evolution, a mark of cognitive superiority. But the sea otter demonstrates that the essence of intelligence lies not in invention, but in transmission, the ability to pass knowledge forward. Each generation adds to a collective memory of technique and refinement. The sound of shell against stone echoing across the kelp beds is the rhythm of continuity. It is culture distilled into motion. Beneath this intelligence lies remarkable physiology. The otter's forelimbs are highly articulated, capable of intricate movement and fine manipulation. Muscles and tendons allow for dexterity rare among marine mammals, while sensory whiskers detect subtle vibrations in the water, helping locate hidden prey. Its lungs and diaphragm are adapted for frequent dives, rapidly exchanging gases to sustain a metabolism that burns almost constantly. Its digestive system is streamlined for efficiency, extracting energy with minimal waste. Every part of its anatomy is optimized for a life of learning, movement, and relentless feeding, a machine for adaptation disguised as a ball of fur. As dusk settles over the coast, the kelp forest sways under the push and pull of the tide. The mother finishes her foraging and returns to her pup, the stone still clutched beneath her arm. She feeds, then grooms the pup's fur, rolling and spinning in the fading light. The two drift together, bound by a strand of kelp, surrounded by the sound of distant waves and the faint tapping of other otters at work. Within this floating school, lessons continue in silence. Each strike, each dive, each demonstration shaping the next generation of teachers. In the soft rhythm of shell and stone, the sea otter embodies the intelligence of persistence. It is an animal that carries its classroom wherever it goes, building knowledge not with words but with actions, shaping both its young and its ecosystem through the mastery of craft. The kelp forests rise and fall with the tide, the urchins scatter, the currents shift, but the tapping continues. The ocean's smallest architect, hammer in paw, keeps teaching the language of survival one shell at a time. The open ocean stretches vast and unbroken, a blue desert with no landmarks, no shadows, and no fixed borders. Yet somewhere within this endless space, a giant ray glides with unerring confidence, following a route that only it seems to know. The manta ray, broad as a small aircraft and graceful as drifting silk, is both wanderer and navigator. It crosses thousands of kilometers of open sea and yet returns year after year to the same coral ridges, the same cleaning stations, and sometimes even the same hour of the day. In a realm without roads, the manta remembers. Its journeys are not random drifts through water, but deliberate paths through memory, a living map written in instinct, intelligence, and perhaps something more elusive: awareness. To understand a manta's world, one must first enter the light. Near the surface, sunlight filters down through miles of clear ocean, scattering into shifting ribbons that dance across its back. The animal seems to fly rather than swim, using its massive cephalic fins, those curled horn-like extensions near the mouth, to funnel plankton-rich water toward its gaping maw. Every motion is measured and efficient. With each slow beat of its triangular pectoral fins, the manta glides forward with almost no turbulence. Its skin is smooth and firm, patterned with black and white markings that are unique to each individual, fingerprints of the sea. Researchers can identify mantas by these patterns, and through decades of observation, they've discovered a remarkable truth. Mantas exhibit sight fidelity. They are not aimless drifters, but navigators who remember and return. At first glance, their behavior seems paradoxical. How can a creature so large and apparently simple, a filter feeder of plankton, exhibit such precision in movement and decision-making? The answer lies hidden within one of the largest brains of any fish. A manta's brain is not just large in absolute size, but highly developed relative to its body. Its cerebellum and telencephalon, regions associated with coordination, memory, and social processing, are enlarged in ways comparable to dolphins and some primates. This neural investment hints at advanced spatial learning, long-term memory, and even problem-solving. In controlled experiments, mantas have displayed behaviors suggesting self-awareness, performing repetitive movements before mirrors as if testing whether the reflection corresponds to themselves. Such curiosity is rare among fish, yet mantas seem drawn to novelty, to interaction, to the exploration of cause and effect. But their intelligence is not abstract. It is functional, evolved for survival in a fluid and unforgiving world. The ocean is a shifting mosaic of temperature, current, and productivity, and mantas must remember where and when food will appear. Plankton blooms follow cycles of moon, wind, and season. Cleaning stations, coral outcrops where small wrasses and cleaner fish remove parasites, remain fixed across decades. A manta's roots weave these resources together, forming a mental map as intricate as any migratory birds. Studies using satellite tags have revealed that mantas navigate along consistent corridors that may stretch for hundreds of kilometers, revisiting the same feeding and cleaning sites across years. This fidelity suggests not mere habit, but recognition. The ocean, to a manta, is not blank space, but a network of remembered coordinates. At one such site, a submerged reef in the Maldives, mantas gather as if summoned by invisible signal. The water churns with life. Cleaner wrasses dart between coral heads, surgeonfish hover in anticipation, and the distant hum of plankton currents fills the background. Then, from the blue, the first giant appears. It approaches slowly, circling above the reef before descending with a measured roll, positioning itself perfectly over a cluster of cleaner fish. The small attendants immediately begin their work, picking at the ray's gill openings, removing parasites and dead skin. More mantas arrive, queuing in orderly fashion, each waiting its turn as though following an unwritten code. They circle in holding patterns above the reef, adjusting position to maintain spacing, moving in what appears to be synchronized awareness. These cleaning stations serve as both spa and social hub, a place where mantas interact, communicate, and possibly exchange cues. The calm choreography suggests more than chance alignment. It hints at recognition, at etiquette, even at hierarchy. Sound plays a minimal role here. Mantas are silent. Instead, they rely on body language and position. Subtle shifts of angle, approach, and pacing govern interaction. When a newcomer joins a circle, others adjust their distance automatically, maintaining a fluid equilibrium. The rules of spacing and rotation appear consistent across encounters, learned through experience rather than dictated by instinct alone. In this way, the reef becomes a meeting ground of memory and behavior, a physical manifestation of social order in a species long thought solitary. Beyond these structured gatherings, mantas display complex foraging strategies that reveal cognitive depth. During feeding events, they often form feeding chains, swimming in single-file lines through dense plankton swarms. Each individual follows the turbulence left by the one ahead, using it to direct prey into its open mouth. In larger aggregations, the pattern expands into spiraling formations known as feeding cyclones, where dozens of mantas circle a shared core of concentrated plankton. The mechanics of this coordination are astonishing. Every manta maintains position and spacing, responding in milliseconds to changes in current or density. This synchronization requires acute sensory processing and spatial awareness, a ballet of giants performed in slow motion. Their sensitivity to flow and orientation is enhanced by a network of electroreceptors, tiny gel-filled pores called ampullae of Lorenzini, that detect electric fields generated by prey and movement. Combined with an acute sense of hydrodynamics, these organs allow mantas to read the invisible texture of the water. They can sense eddies, currents, and even the approach of other large animals through minute pressure changes. In a way, the manta perceives the ocean not as emptiness, but as structure, a map of invisible forces sculpted by the physics of motion. What makes their intelligence particularly compelling is how it integrates emotion-like responses. Divers who have spent years studying mantas often report behaviors that suggest curiosity and even recognition. Individuals approach divers, make prolonged eye contact, and sometimes return repeatedly to the same humans over long intervals. While such anecdotes walk the edge between science and story, they reflect an animal unafraid to investigate, to remember, and to choose interaction. In evolutionary terms, curiosity itself is a form of intelligence, a willingness to explore beyond immediate reward. For a manta, this may have adaptive value. Curiosity leads to discovery of new feeding grounds, new routes, new opportunities. From an ecological perspective, mantas occupy a paradoxical niche. They are both keystone species and gentle giants, filter feeders that help regulate plankton populations while linking deep and surface ecosystems. Their migrations connect nutrient cycles across vast distances, redistributing energy from productive coastal zones to open ocean deserts. When mantas dive deep, they bring surface nutrients downward. When they rise again, they excrete nitrogen that fertilizes plankton near the surface. Through these movements, they act as biological conduits, maintaining balance in systems that would otherwise fragment. Their evolutionary path diverged from that of stingrays millions of years ago. Where others evolved ambush strategies and venomous tails, mantas traded weapons for wings. They grew large enough to deter predators, intelligent enough to navigate oceans, and social enough to find safety in numbers. Their size, though immense, does not make them invincible. Orcas occasionally prey on them, and sharks leave scars on their wingtips. But their survival strategy depends less on defense than on awareness. Knowledge, for the manta, is armor. When night falls, the ocean transforms. Moonlight flickers on the waves, and deeper down, bioluminescent plankton shimmer like suspended stars. In this glowing darkness, mantas continue to travel, some alone, some in pairs, tracing routes that cross entire basins. They navigate not by sight but by memory, by temperature gradients, by the invisible geometry of the planet's magnetism. What we see as endless blue, they perceive as patterned familiarity, a cognitive map shaped through experience. It is easy to think of intelligence in terms of tool use or communication, but in the manta, intelligence manifests as orientation, knowing where to be, when to arrive, and how to coexist within a system of others. It is an intelligence distributed through motion, encoded in migration, reinforced by return. Every pass through a cleaning station, every loop of a feeding cyclone, every remembered corridor across the Pacific is a rehearsal of memory, a renewal of the manta's mental cartography. At dawn, the sea begins to glow again, and the giants return to the surface. Their wingtips break the water like curved blades, slicing sunlight into shimmering trails. They circle once, twice, then vanish into the deep, their routes invisible to us, but as familiar to them as the coastline is to a sailor. Somewhere in that boundless expanse, a manta glides toward a reef it has not seen for a year, but remembers perfectly. The ocean for it is not vast or empty. It is mapped in experience, traced in memory, and alive with meaning. And so, among all the creatures of the sea, the manta ray stands as one of its quiet intellectuals, a mind without words, a traveler without borders, carrying the ocean's geography not in charts or stars, but in the living circuits of its brain. The water is thick with suspended sand, a grey haze that swirls and shifts with every pulse of the tide. Visibility is poor, barely a few body lengths, and yet something moves with certainty through this shifting fog. A shape glides just above the seabed, heavy-bodied but unhurried, its outline fading in and out of the gloom. The tiger shark has arrived. It patrols the shallows like a ghost written in muscle, guided not by sight, but by a suite of senses that make murk an ally rather than a hindrance. This is a hunter that remembers, a predator whose mind holds a mental chart of coasts, currents, and the rhythms of prey. In these waters, every movement is informed by memory as much as instinct. The tiger shark is among the most versatile predators in the ocean, a biological generalist in a world of specialists. Its reputation as an indiscriminate eater is well earned. It will consume almost anything that fits in its mouth, from sea turtles to seabirds to refuse from human hands. But beneath that image of chaos lies a sophisticated logic. Individual sharks show distinct preferences for certain prey types and hunting grounds, returning year after year to the same coastal routes, the same nesting beaches, the same estuarine channels. They are not drifters but deliberate travelers, guided by patterns learned over time. This fidelity to place, site-specific hunting anchored in experience, reveals a dimension of shark cognition often overlooked: memory. Each year, as the seasons turn, tiger sharks trace long migratory circuits that synchronize with the life cycles of their prey. In the western Atlantic, they move northward in summer, following the warming currents and the migration of sea turtles. When the turtles return to their nesting beaches to lay eggs, the sharks arrive almost on schedule, patrolling just beyond the breakers. Researchers tracking tagged individuals have found remarkable consistency. Some sharks return to the same beaches within days of the previous year's arrival. It is a strategy built on anticipation. They are not following scent trails in real time, but recalling where and when food will appear. This ability to predict seasonal abundance suggests long-term memory, a kind of mental calendar woven from years of repetition. Memory for a shark is more than a passive record. It is a survival tool shaped by an environment that rarely forgives mistakes. In turbid coastal waters, where vision is useless and sound muffled by sediment, the tiger shark relies on a combination of smell, electroreception, and hydrodynamic sensitivity. Its snout houses the ampullae of Lorenzini, tiny jelly-filled pores that detect the faintest electrical fields emitted by living tissue. Even a heartbeat beneath sand registers as a pulse of data. Over time, these encounters form spatial patterns. The shark learns which areas of a bay yield buried rays, where current flows concentrate drifting carrion, and where turtle traffic is highest under moonlit tides. These are not random wanderings, but the markings of a route built through learning. The ocean may appear featureless, but to a shark's mind, it is mapped in signals, temperature gradients, magnetic cues, and remembered successes. Off the coasts of Hawaii, tagged tiger sharks have been documented traveling across hundreds of kilometers of open ocean to revisit specific seamounts, underwater mountains invisible from the surface. These submerged landmarks often support bursts of productivity, attracting fish, seabirds, and turtles. The shark's precision in locating them hints at magnetoreception, an ability to sense the Earth's magnetic field and use it like a compass. Combined with memory, this internal navigation system allows them to maintain fidelity to favored routes even after years away. Like migratory birds, they may imprint on magnetic coordinates during early life, returning as adults to the same feeding grounds. The ocean, vast as it is, becomes a familiar landscape once decoded through experience. The tiger shark's flexibility is what makes it so resilient. Unlike the great white, which relies heavily on visual ambush and prefers cooler, clear waters, the tiger thrives in variety. In crystal shallows, it uses stealth, approaching from below in sudden bursts. In muddy bays, it shifts to scavenger mode, following scent and vibration instead of sight. When hunting in coral reefs, It moves with care, weaving through channels that conceal both prey and danger. This adaptability is cognitive as much as physical. The shark modifies its behavior to match environment, a hallmark of learning. Observations have shown individuals adjusting strike angles, timing, and approach based on the visibility and behavior of prey. Each hunt is a calculation, a decision-making process balancing risk and reward. Among its favored prey, few challenge its skill like sea turtles. The turtle's shell may seem like perfect armor, but the tiger shark has learned to exploit its weakness. With a powerful lateral strike, it flips the turtle upside down, exposing the vulnerable underside where the shell is thin. The precision of this maneuver suggests not mere reflex, but experience. Younger sharks lacking practice often attack clumsily, biting the carapace without success. Adults learn to approach at specific angles and target soft tissue first. Over time, these tactics refine into expertise, passed not through teaching, but through observation and repetition. The shark's success rate increases as its memory fills with encounters, lessons written in muscle and motion. The tiger shark's role in the ecosystem extends far beyond its reputation as a scavenger. It regulates populations of sea turtles, dugongs, and rays, maintaining the balance of marine vegetation and prey communities. In places like Shark Bay, Australia, the mere presence of tiger sharks shapes the behavior of other animals. Dugongs and turtles alter their grazing patterns to avoid areas where sharks patrol, preventing overconsumption of seagrass meadows. Ecologists call this the landscape of fear, an invisible boundary created by predator memory and prey awareness. The shark does not need to kill to influence. Its consistency alone reshapes the behavior of the ecosystem around it. And yet, the tiger shark's intelligence is not rooted in sociality. Unlike dolphins or orcas, it lives largely alone. Its learning comes from the slow accumulation of individual experience, not from cooperation. Each shark builds its own archive of knowledge, the location of safe resting areas, the timing of seasonal upwellings, the behavior of specific prey. This solitary intelligence, memory shaped by feedback and trial, is perhaps one of the purest forms of instinctive learning in the ocean. It demonstrates that cognition need not be social to be sophisticated. Their sensory perception borders on the extraordinary. In addition to electroreception, tiger sharks possess an acute sense of smell, capable of detecting blood concentrations as low as 1 part per 10 billion. Their eyes, adapted for dim light, contain a reflective layer called the tapetum lucidum that amplifies vision in darkness. Combined, these senses allow them to hunt effectively from shallow reefs to depths exceeding 1,000 meters. Yet even these biological tools are sharpened by practice. A shark that hunts in bright coral-rich water relies on contrast and movement. One that lives in deep, low-light zones learns to interpret faint bioluminescent glows and changes in water temperature. Behavior and physiology intertwine, evolving together through experience. When viewed from above, the tiger shark's pattern, dark stripes fading along its flanks, resembles the shifting shadows of surface light. These markings serve as camouflage, breaking up its outline against both sunlit shallows and open blue. They also hint at youth. The stripes are most pronounced in juveniles and fade as they age, suggesting that even appearance adapts to lifestyle. Younger sharks inhabit shallower, riskier coastal zones where camouflage is essential. Adults, larger and more dominant, range further offshore, relying less on concealment and more on command. Age, size, and learned confidence shape how each shark perceives and moves through its territory. Despite its reputation, the tiger shark is not reckless. It is methodical, calculating, and often cautious. Before attacking, it may circle potential prey several times, bumping or brushing it to gauge reaction. This bump and bite behavior is a form of tactile investigation, a test, not a blind strike. Through contact, the shark gathers data on size, movement, and density, adjusting its attack accordingly. In this way, touch becomes another extension of perception. It is the ocean's version of inquiry, a predator's way of asking questions before committing to action. As the tide turns and the moon rises over the horizon, the shark resumes its patrol along the outer reef. Its path mirrors those of countless nights before, tracing invisible lines known only to it. The water glows faintly under moonlight, but the shark needs no light to know where it is. Each current, each temperature gradient, each familiar vibration is a cue embedded in memory. Somewhere ahead, the turtles are nesting again, their rhythmic labor syncing with an ancient predator's clock. The shark does not think of it as return. It simply is return, guided by a pattern older than thought, but refined by experience. In this solitary hunter, the ocean's intelligence takes on its most primal form, memory made flesh. The tiger shark's knowledge is written not in words or symbols, but in motion, in the routes it retraces, the choices it perfects, and the ecosystems it quietly shapes. Every coast it visits, every current it follows, every prey it learns to predict, is part of an ongoing study, a curriculum of survival taught by the sea itself. It is a student of tides, a cartographer of prey, and a master of adaptation. And when it finally disappears into the grey, leaving only the fading pulse of its wake behind, what remains is not fear, but understanding. The tiger shark endures not because it is the strongest or fastest, but because it remembers. Because every hunt, every migration, every turn of the current adds another line to the ocean's oldest memory. That knowledge, not chance, rules the deep.
Night falls gently on a tropical shore. The sand glows faintly beneath a wash of starlight, and the sound of the surf arrives in rhythmic intervals, steady, deliberate, like the beating of a heart.
Then, from the darkness beyond the tide line, the sand begins to stir. A hatchling green sea turtle, scarcely larger than a human palm, pushes its way to the surface. Around it, dozens of siblings emerge in synchronized bursts, driven by a shared urgency that evolution has refined across millions of years. Within moments, the beach is alive with movement, tiny bodies flailing, scattering, all drawn toward the faint shimmer of light reflecting off the ocean.
This is instinct in its purest form, but hidden within that instinct is something deeper, a navigation system that will guide this hatchling and others like it across entire oceans and back again decades later. It is a journey inscribed not in sight or sound, but in the invisible pull of the earth itself. The green sea turtle's migration is among nature's most astonishing feats of memory. Born on a single patch of sand, each turtle somehow imprints on the precise magnetic signature of that location, a unique combination of field intensity and inclination angle produced by the planet's molten core. This geomagnetic fingerprint acts as an address, encoded into the turtle's nervous system during the brief moments after hatching. Years later, as a mature adult thousands of kilometers away, the turtle will use that same magnetic data to return to its birthplace with near-perfect accuracy. Scientists call this process geomagnetic imprinting, and though its mechanism remains partly mysterious, its results are undeniable. The turtles that once left this beach as hatchlings will one day crawl ashore here again, guided by forces imperceptible to human senses. For now, though, the newborn faces the first test of its education, the dash to the sea. The moon and stars cast faint celestial cues across the horizon, and the hatchling's eyes, adapted to detect the brightest open vista, interpret this glow as safety. It scrambles toward it, propelled by instinct and adrenaline. Each step across the sand is fraught with risk. Ghost crabs wait in burrows, ready to seize the unwary. Shorebirds patrol the air. Even the heat itself, radiating from the day's sun, can disorient or exhaust the smallest travelers. For every 1,000 hatchlings, perhaps one will survive to adulthood. Yet each survivor carries within it an archive of experience, a record that will shape its lifelong syllabus of navigation. Once in the water, the young turtle becomes part of what researchers call the lost years, a period when juveniles drift invisibly through vast oceanic currents, their whereabouts largely unknown. For years, they ride the North Atlantic gyre or other circulating currents, feeding on plankton and small jellyfish, growing slowly in the pelagic wilderness. During this time, they refine their navigational abilities, not through conscious learning, but through the steady accumulation of sensory feedback. They encounter gradients of temperature, salinity, and chemical composition, each an environmental marker stored subconsciously in the brain.
Magnetic cues form the backbone of their orientation, but as turtles mature, they integrate additional information. Celestial patterns, the polarization of light at the horizon, and even olfactory cues, subtle chemical signatures carried by ocean currents, become reference points. Navigation becomes multi-layered, a composite of environmental memories continuously cross-checked against a magnetic map. The concept of geomagnetic imprinting implies a kind of innate cartography, but the turtle's precision depends on calibration. Magnetic fields drift slightly over decades, and coastlines shift with tides and erosion. To compensate, adult turtles refine their routes with experience. Tagging studies have revealed that individual females returning to nest adjust their paths across years, correcting deviations as if updating a mental map. They do not follow static coordinates but dynamic pathways, routes shaped by both memory and environmental feedback. This ability to adapt distinguishes learned navigation from mere instinct. It demonstrates not just orientation but cognition, the capacity to reconcile expectation with observation, to learn through iteration. As adults, green sea turtles embark on migrations spanning thousands of kilometers between feeding grounds and nesting beaches. In the Caribbean, individuals forage on seagrass beds off the coast of Nicaragua, yet travel across open ocean to nest on beaches in Costa Rica. In the Pacific, they swim from the Galapagos Islands to the shores of Mexico, crossing currents and temperature fronts that would confound most marine animals. During these migrations, the turtles use multiple sensory systems in concert. Magnetic fields provide a general bearing: north, south, east, west, while celestial cues, such as the position of the sun, refine their heading. Chemical gradients too play a role near the coast. Researchers have found that turtles can detect specific odor plumes released by their natal beaches, perhaps derived from decaying vegetation or microbial activity unique to each site. These plumes function as olfactory signposts, confirming that they have arrived not merely at the right coastline, but at the right few hundred meters of it. Their sense of spatial awareness extends beyond navigation to habitat fidelity. Adult green turtles show remarkable loyalty to specific foraging grounds, revisiting the same seagrass meadows year after year. These areas act as both feeding sites and rest stops between migrations. By grazing selectively, turtles help maintain the ecological health of these meadows. Seagrass grows quickly but can smother itself if left unchecked. The turtle's grazing trims the blades, promoting regrowth and oxygen flow, essential for maintaining carbon sequestration in coastal ecosystems. In this way, their migratory habits do more than sustain individuals, they sustain landscapes. Each turtle functions as a gardener of the sea, linking distant habitats through cycles of movement and feeding. Underwater, their motion is both powerful and efficient. The green turtle's shell, or carapace, is streamlined for long-distance travel, reducing drag while protecting vital organs. Their lungs are enormous relative to body size, allowing deep dives lasting up to 5 hours under cold conditions. They regulate buoyancy by adjusting air volume and body position, ascending and descending with subtle shifts in posture rather than constant motion. Their slow metabolism allows them to survive on modest resources during migration, but once they reach feeding grounds, their appetite becomes relentless. Feeding on seagrass and algae, they derive energy from a plant-based diet unusual among marine reptiles, relying on symbiotic gut bacteria to break down cellulose. This adaptation marks an evolutionary transition from carnivory to herbivory, a shift that likely co-evolved with the expansion of seagrass ecosystems millions of years ago. When nesting season arrives, the turtle's internal compass awakens. Guided by magnetic memory, females return to their natal beaches, often within a few meters of where they themselves hatched decades earlier. The process is arduous. They may travel thousands of kilometers, fasting for weeks, crossing open ocean and battling unpredictable weather. When they finally arrive, they wait offshore until nightfall, then crawl onto the beach in labored, deliberate motion. The act of nesting is instinctive, yet the precision of location is learned, a culmination of sensory synthesis. With powerful flippers, the female excavates a deep chamber, deposits her eggs, and covers them carefully before returning to the sea. The cycle begins anew, and another generation of hatchlings will one day inherit her invisible maps. This fidelity to birthplace, known as natal homing, is more than reproductive routine, it is ecological continuity. Each generation reinforces the stability of specific nesting beaches, maintaining population structure and genetic diversity across regions. When these turtles vanish, as they did during past centuries of overhunting, ecosystems unravel. Seagrass meadows grow dense and decay, coral reefs lose nutrient cycling, and predators like tiger sharks lose a key prey source. The turtle's migratory memory, therefore, becomes part of the ocean's memory, a living archive of interconnected systems. Modern science has begun to decode the neural basis of this ability. In the turtle's brain, specialized magnetite crystals may act as microscopic compass needles, aligning with the Earth's field and sending directional signals to sensory neurons. These signals, processed in the trigeminal nerve and midbrain, translate into spatial orientation. In experiments, disrupting magnetic cues with artificial fields causes disorientation, confirming that turtles interpret magnetic information directly rather than through secondary cues. What remains remarkable is the resolution of their perception. They can detect differences in magnetic inclination of less than 1/10 of a degree, a precision comparable to advanced instrumentation. As dawn approaches, the tide rises over the nesting beach once more. The faint outlines of turtle tracks carve temporary patterns into the sand, soon to be erased by waves. Beneath the surface, the next generation of embryos begins to stir, already influenced by the temperature of the sand that determines their sex. Warmer nests, producing females, cooler ones males. Even before birth, their environment is teaching them. The magnetic field above their heads, the chemical scent of the shoreline, the gradient of light on the horizon, all are subtle lessons encoded into memory. Their education begins in silence under sand, guided by forces that transcend sensory boundaries, and so the cycle continues. The ocean's ancient students return to their classrooms not by sight, not by sound, but by memory inscribed in magnetism. The green sea turtle's journey is a lesson in precision and persistence, a testament to how evolution sculpts intelligence through repetition and necessity. Each migration, each return, each hatchling crawling toward the sea adds another line to an unbroken syllabus that began millions of years ago and still unfolds today, written across the invisible grid lines of the planet itself. The reef at dawn hums with quiet energy. Shafts of sunlight pierce the shallows, refracting through moving water and scattering in 1,000 hues across coral heads. Among this kaleidoscope of life, the anemones sway, pale tentacles rippling gently in the current, each one armed with stinging cells capable of paralyzing most creatures that dare to touch them. And yet, nestled among those lethal arms, bright flashes of orange and white dart confidently. Clownfish, tiny, territorial, and fiercely intelligent, move through their poisonous fortress as though it were a living home. To the untrained eye, it looks like safety by chance. But beneath the anemone's soft canopy lies one of the most structured societies in the ocean, an underwater microcosm of hierarchy, cooperation, and biological negotiation. The relationship between clownfish and sea anemones is one of the most iconic examples of symbiosis in marine biology. It is a partnership built on chemical truce and evolutionary precision. The anemone, with its venomous tentacles, gains protection from butterfly fish and other predators that would otherwise tear at its flesh. The clownfish, in return, finds sanctuary from the reef's endless threats, moray eels, groupers and wrasses that see it as an easy meal. Yet this alliance is not purely defensive. The clownfish cleans debris from the anemone, fans oxygenated water through its tentacles, and even delivers nutrients through its waste. In return, the anemone's stings deter all but the most determined intruders. This balance of labor creates a stable unit, a self-contained micro-reef where the line between host and inhabitant blurs. But the true intrigue lies in how these colonies are governed. Each anemone typically hosts a small group of clownfish, a single breeding pair, and several subordinates. This social structure follows a rigid hierarchy based on size, not age. At the top is the largest individual, the dominant female. Beneath her is the slightly smaller male, her mate. Below them are juveniles and non-breeding subadults arranged in descending order of size. The hierarchy is absolute. Only the top pair reproduces, while the rest live in enforced waiting, a queue system that dictates not just social rank, but biological destiny. Clownfish societies function through remarkable hormonal regulation. Every individual is born male, but their reproductive status is suppressed through chemical signals and social behavior. The dominant female maintains her position through aggression and subtle hormonal control, releasing pheromones that inhibit the development of others around her. Should she die, the hierarchy shifts instantly. Her mate transforms into a female through a process known as sequential hermaphroditism, a biological metamorphosis triggered by hormonal change, and the largest subordinate male ascends to breeding status. In this way, the system is self-perpetuating, ensuring continuity without the need for immigration or new pair formation. It is a reproductive strategy as efficient as it is ruthless. The queue system enforces peace through constraint. Subordinates never grow large enough to challenge their superiors. Doing so would disrupt balance and risk expulsion. Growth suppression is achieved through both social stress and endocrine regulation. The dominant individuals feed more, enjoy lower stress hormone levels, and actively limit access to food for lower ranks. Those beneath them modulate their own growth, slowing metabolism to avoid confrontation. In the confined world of the anemone, size is both weapon and shield. To grow too quickly invites eviction. To remain too small invites predation. Evolution has tuned this delicate equilibrium through countless generations, producing one of the most stable social hierarchies known among fishes. Daily life in this miniature society revolves around maintenance and vigilance. Each morning, the group emerges from the tentacles to clean their home. Using their fins, they remove debris and aerate the anemone's tissues, improving its respiration and preventing sediment buildup. This cleaning behavior is not mere hygiene. It enhances the anemone's health, ensuring the colony's continued protection. When intruders approach, the entire group responds with coordinated aggression. Subordinate fish dart out in short bursts, nipping and displaying in unison, while the dominant female monitors from behind. The choreography is precise and learned. Individuals memorize the response patterns of their superiors, practicing them through observation and imitation. In this sense, clownfish societies function as schools as well as hierarchies, learning environments where every act of defense or feeding reinforces social order. The relationship extends to anemone selection, a crucial choice that determines the colony's survival. Not all anemones are suitable hosts. Each clownfish species has specific preferences, shaped by evolutionary compatibility with particular anemone toxins. The fish acquire immunity through gradual acclimation. When a juvenile first encounters an anemone, it performs an intricate dance of contact and retreat, brushing against the tentacles in controlled passes. During this ritual, the fish coats itself with the anemone's mucus, disguising its own chemical signature until it is recognized as part of the host. A premature touch would result in death, but the process of gradual exposure teaches the young fish the boundaries of its new home. Once accepted, it rarely leaves. The partnership is exclusive, often lasting for the lifetime of the anemone itself, which can span several decades if undisturbed. Within this protected world, communication is constant and nuanced. Clownfish produce a range of clicks and pops generated by snapping their jaws and grinding their teeth. These sounds are not random. They convey dominance, submission, and alarm. The dominant female emits loud, pulsed signals that reinforce hierarchy, while lower-ranking individuals respond with softer, faster clicks to indicate compliance. This acoustic system, though primitive by human standards, functions as an effective social language. Combined with visual posturing, fin displays, head shakes, and body vibrations, it maintains order without continual conflict. The physical dynamics of their environment also shape their behavior. The anemone's tentacles expand and contract with temperature, light, and water flow, altering the available space within its canopy. When the tentacles retract during cooler periods or at night, competition intensifies. Subordinates are pushed to the edges, more exposed to predators. These spatial pressures reinforce hierarchy. The safest inner zones belong to the dominant pair, while younger members must risk the periphery. In this way, even the anemone's physiology enforces the colony's social structure. Outside the safety of their host, clownfish live brief and perilous lives. Studies have shown that individuals expelled from their colony survive, on average, only a few days before predation. This dependency creates what behavioral ecologists call ecological monopolization, a situation where the cost of leaving exceeds the cost of submission. The result is a society in which cooperation arises not from altruism, but from necessity. By accepting subordination, younger fish secure a chance, however slim, at eventual inheritance of the anemone. Every act of restraint is, in evolutionary terms, an investment in the future. Yet the benefits of this social precision ripple outward through the ecosystem. Anemone colonies occupied by clownfish show higher rates of oxygen exchange, lower parasitic loads, and faster growth compared to those without residents. The constant cleaning and aeration stimulate photosynthetic efficiency in the symbiotic algae living within the anemone's tissues. In return, healthier anemones provide greater refuge and feeding stability for the clownfish. This feedback loop illustrates a larger principle in reef ecology. Cooperation, even at small scales, amplifies productivity across systems. The clownfish and anemone together form a self-sustaining micro-habitat, an island of stability in an otherwise competitive and shifting world. Despite their colorful simplicity, clownfish embody complex social intelligence. Their ability to maintain order through non-lethal hierarchy, regulate growth hormonally, and modulate reproductive roles according to circumstance rivals the social adaptability of birds and mammals. Their entire existence hinges on rule following, yet those rules are flexible enough to preserve group cohesion through environmental upheaval. If a storm dislodges an anemone, the colony relocates as a unit, searching for another suitable host. Individuals remember the chemical signature of their previous anemone, using it to identify compatible species nearby. Once a new home is found, the same hierarchy re-establishes itself, as though transplanted intact. From a broader perspective, the clownfish's world is a study in scale. Beneath a few square meters of reef, the same evolutionary principles that govern lions on the savanna or wolves in the tundra unfold in miniature. There is dominance and submission, competition and cooperation, inheritance and mortality, all condensed into a single pulsating anemone. What appears at first as decorative coral life is, in truth, an elaborate system of governance, enforced by biology and sustained by behavior. As evening returns and the reef dims, the clownfish retreat deep into their host. The tentacles close protectively around them, sealing off the tiny world they have built. Outside, predators begin to stir, and plankton clouds rise through the darkening water. Within the anemone's folds, the group rests, their hierarchy unbroken, their routines unchanged. Tomorrow they will clean again, defend again, wait again, each member holding its place in a lineage that endures through discipline and design. In the silent governance of this micro-reef, there are no rebellions, no coups, no accidents of rule. There is only the rhythm of maintenance and inheritance, a living constitution enforced not by law but by evolution. The clownfish live by rank and rule, and in doing so, they preserve a small, perfect order in the chaos of the coral world, a classroom where cooperation is survival, and where every lesson is written in the language of restraint. The reef is still in the early light of morning, its surface a kaleidoscope of motion and shimmer. Schools of silver-side fish flash like molten mirrors, and coral heads breathe soft plumes of detritus into the current. Among this living architecture, where every hole and crevice hides something waiting, a small but formidable creature lurks, half buried in sand, claws folded like concealed weapons. The mantis shrimp, though no longer than a human hand, rules its burrow with the quiet confidence of an apex predator scaled down to miniature. Its vision alone sets it apart from nearly all others, eyes perched on mobile stalks, each capable of independent movement, scanning the spectrum of visible and invisible light. What the mantis shrimp sees is a world none of us can imagine, one painted not only in color but in polarization, an extra layer of light physics that most animals, and even humans, are blind to. In the territory of mantis shrimps, the boundaries between combat and communication blur. These crustaceans live solitary lives in burrows carved into coral rubble or sandy slopes, defending their patch of seabed from rivals of their own kind. But unlike many territorial species that fight to exhaustion or death, mantis shrimps operate on a subtler level of diplomacy. Their disputes are negotiated through a hidden language of light, patterns of polarization reflected off their armor-like exoskeletons, visible only to others of their kind. To an outsider, they appear iridescent, but to another mantis shrimp, those hues encode status, threat level, and identity. Every confrontation is preceded by a display, a silent exchange of polarized passwords that can diffuse violence before it begins. This optical language relies on one of the most complex visual systems in the animal kingdom. Each eye of a mantis shrimp contains up to 16 photoreceptor types for color, compared to the 3 in humans, and additional receptors dedicated to polarized light. These specialized cells, aligned at precise microscopic angles, detect the orientation and phase of light waves bouncing off surfaces. To the shrimp, the sheen on a rival's exoskeleton isn't just bright, it carries directional data, like a visual barcode of intent. By rotating their eyes and adjusting viewing angles, they can interpret these polarization cues from any direction, allowing instant recognition even in dim or turbid water. The same system helps them hunt by revealing transparent prey, like shrimp larvae, and by piercing the camouflage of soft-bodied animals whose skin scatters light unevenly. For a creature armed with one of the fastest and most destructive strikes in nature, restraint might seem unlikely. Yet mantis shrimps, particularly the smasher species, exhibit surprising levels of self-control and tactical awareness. Their raptorial appendages, modified forelimbs resembling spring-loaded clubs, can accelerate faster than a bullet leaving a gun barrel, producing forces strong enough to shatter snail shells and crack aquarium glass. But such power comes with risk. The strike mechanism is delicate and metabolically costly to repair. A broken club could mean starvation. Thus, rather than resort immediately to violence, rival mantis shrimps often engage in ritualized sparring, a contest of endurance, not destruction. These confrontations unfold like a gladiatorial dance. 2 individuals face each other, claws raised in threat displays, eyes rotating constantly to monitor angles. Each shrimp performs merrill spreads, lifting its raptorial limbs wide to expose bright patches of color hidden on the inner surface. These markings function as visual amplifiers of strength, warning signals designed to prevent escalation. Sometimes the display alone is enough. One opponent retreats, acknowledging inferiority. If neither yields, they may begin controlled striking contests, trading measured blows to each other's armored carapaces. The goal is not to injure, but to assess. By delivering and withstanding strikes, each shrimp gathers information about the other's power and endurance. These ritualized duels reduce unnecessary fatalities, conserving both individuals for future survival. Over time, these interactions build memory, a social record encoded not in alliances but in recognition. Neighboring mantis shrimps remember each other's strength, character, and even rhythm of movement. Scientists call this phenomenon the dear enemy effect. Once 2 rivals have established their boundaries, future encounters tend to be less aggressive. They recognize each other's polarized signals, recall prior outcomes, and often resolve disputes with minimal display. In an environment where every joule of energy matters, remembering who is worth fighting saves time and life. This capacity for individual recognition, rare among crustaceans, suggests a level of cognitive sophistication not commonly attributed to invertebrates. The mantis shrimp's intelligence extends beyond conflict. Inside their burrows, they maintain intricate homes, chambers carved with precision, lined with coral fragments, and defended like fortresses. Some species close their entrances with rubble at night, a barricade against nocturnal predators. Others, especially those living in pairs, divide labor. One guards the entrance while the other tends to eggs. Mantis shrimps form monogamous bonds that can last for years, an unusual trait among marine invertebrates. They coordinate feeding schedules and defend territory together, communicating through vibrations and visual cues. Polarized light plays a role here too. The subtle gleam along an appendage or body band helps mates recognize each other in the dense complexity of the reef. Their hunting behavior reveals yet another layer of precision. A smasher mantis shrimp may wait motionless outside its burrow, sensing faint vibrations of approaching prey through its antennae. When a crab or snail wanders too close, the shrimp unleashes its strike, a blur of motion invisible to the human eye. The impact generates not only physical force but also cavitation bubbles, tiny pockets of vapor that collapse with explosive energy, producing shock waves and flashes of heat that can reach thousands of degrees Celsius in microbursts. The result is double impact, the mechanical blow followed by the implosion of the cavitation bubble. Through experience, individual mantis shrimps learn to adjust timing and angle, refining their aim across hunts. Each strike, successful or not, informs the next, evidence of adaptive learning in a brain smaller than a grain of rice. Their sensory world extends far beyond the visible. The mantis shrimp's compound eyes can move independently, scanning with trinocular vision, each eye perceiving depth on its own. This allows extraordinary spatial awareness, crucial for both hunting and defense. When they aim a strike, their eyes fix and track in microsecond coordination, ensuring accuracy despite the water's distortion. Combined with their polarized vision, this capability turns them into near-perfect hunters, able to detect prey invisible to almost all other predators. But what evolution forged for predation also serves diplomacy. In a densely populated reef, where visual clutter overwhelms most animals, the ability to perceive polarization offers a private communication channel, one that eavesdroppers simply cannot access. In this secret world of polarized light, mantis shrimps broadcast their moods like coded radio signals. Males flash distinct polarization angles during territorial patrols. Females emit subtler reflections that mark reproductive readiness. Even their armor changes reflectivity after molting, temporarily altering how they appear to others. For newly molted individuals, soft, vulnerable, and unable to fight, the reduced polarization acts as a temporary camouflage, a passive signal that says, "not ready." This dynamic modulation of appearance is one of nature's most remarkable examples of adaptive communication, balancing transparency and deception in equal measure. The reef itself amplifies these subtleties. Sunlight filters through the water at oblique angles, scattering polarization patterns that change with time of day. A mantis shrimp positioned at a burrow entrance interprets not only the reflections from its neighbor, but the shifting polarization of the environment, adjusting posture and display accordingly. This contextual awareness, interpreting signal within background, demonstrates a form of visual intelligence previously thought beyond crustaceans. In essence, mantis shrimps read the polarization weather of their surroundings, choosing when to signal and when to remain hidden. Ironically, the same tools of communication that prevent conflict can also trigger it. During breeding season, overlapping territories bring multiple males into proximity, and the normally restrained duels escalate. The airless water thrums with the sound of impact, low-frequency pulses audible even through meters of coral. The shrimp strikes are so fast that they produce flashes of light, microbursts of sonoluminescence. To other species, these flashes mean nothing, but to another mantis shrimp, they may signify danger or dominance. The reef, briefly, becomes a stage of violence contained by memory. Each participant learns the price of persistence and the reward of restraint. As the day fades and the reef darkens, the mantis shrimp retreats into its burrow. Its eyes, still moving independently, scan the last fragments of polarized light dancing above. The signals that once guided battle and boundary now dissolve into dusk. Within minutes, the creature seals itself inside, pulling sand and rubble across the entrance. The reef hums on, fish settling into coral crevices, crustaceans scuttling across rocks. But inside the burrow, the mantis shrimp rests, its claws folded under, its mind cataloguing the day's events. It will remember the rivals it met, the displays it saw, the strikes it exchanged. When dawn comes again and light filters back through the sea, Those memories will guide its choices: who to challenge, who to ignore, and who to trust. Beneath the riot of coral and color, an invisible network of relationships persists, coded not in sound or scent, but in the polarized shimmer of reflected light. In the end, the mantis shrimp's world is both violent and diplomatic, simple in size yet profound in complexity. It is a world where knowledge is survival, where understanding the language of light determines whether to strike, to yield, or to live another day. And though few creatures can see the signals it sends, the reef itself seems to respond, as if acknowledging that in these flickers of polarized brightness, the ocean keeps one of its most intricate conversations alive. The reef stirs with the first light of day. Rays of gold break through the surface, scattering into trembling bands that ripple across the coral. Schools of antheas shimmer like living dust, flashing orange and violet as they twist through the water column. Beneath this bright chaos, a shadow glides with deliberation, broad-headed, thick-bodied, eyes forward. The grouper moves as if measuring the reef itself, charting the geometry of stone, crevice, and current. It is not a wanderer, but an observer, a tactician who knows every contour of its world. Where other fish react, the grouper calculates. This carnivorous giant of coral and rock may appear slow, but it is a predator built on precision. Its heavy body conceals a mind capable of spatial reasoning and social strategy, a rare combination among fish. The grouper's hunting success depends less on speed and more on the geometry of ambush. Every coral buttress, every overhang, every sand chute is part of its mental map. Through repetition, it learns the patterns of its prey. When small reef fish emerge from hiding, where wrasses pause to feed, how currents funnel shrimp into predictable flows. It waits in silence, fins barely moving, suspended in perfect neutral buoyancy. Then, with a sudden vacuum of motion, it opens its mouth. The grouper's strike is an exercise in fluid dynamics. Instead of chasing prey, it creates a weapon out of water itself. Its jaws expand outward and backward at lightning speed, forming a low-pressure cavity that sucks the victim directly in. The suction is so powerful that small fish caught in its field of influence cannot escape even by swimming away. They are drawn into the predator's throat before they realize the danger. But what makes the grouper extraordinary is not this raw efficiency. It is the way it recruits others to hunt alongside it. Across coral reefs from the Red Sea to the Caribbean, groupers have been observed engaging in one of the most remarkable examples of interspecies cooperation in marine life. When prey hides beyond the grouper's reach, wedged deep within coral tunnels or crevices, the grouper seeks assistance. It performs a series of unmistakable headshakes, a repetitive gesture directed toward nearby moray eels. If the eel responds, the grouper swims toward a specific crevice and hovers, its body angled forward and its head thrust into the gap. The meaning is clear. The prey is in here. The eel, long-bodied and serpentine, slips inside while the grouper blocks the other exit. Within moments, the fleeing victim is flushed out into open water and swallowed whole. This alliance between grouper and moray eel is one of the ocean's most studied examples of coordinated hunting between species. It requires communication, trust, and shared timing, traits once thought beyond the cognitive reach of fish. The grouper's signaling gestures are consistent and deliberate. A head shake near a moray is an invitation. A head-first dive toward a coral crevice is a pointer, directing attention to hidden prey. In controlled experiments, morays respond only to these specific gestures, not to random movements. When groupers hunt with eels, their success rate doubles. For the eel, the benefit is access to prey flushed from open water, something its ambush-oriented anatomy rarely allows. Even more fascinating is the grouper's memory for partnerships. Individuals appear to recognize familiar morays and will preferentially recruit the same partners over time. This suggests not just instinctive behavior but learned association. The grouper remembers who responds and who hunts effectively, forming what could be described as working alliances. In the vast and shifting world of coral reefs, this ability to form repeated cooperative relationships is evolutionary gold. It transforms opportunism into a repeatable strategy. But the grouper's intelligence extends beyond cooperation. It demonstrates spatial planning in ways that border on tactical reasoning. Researchers studying coral reef groupers have documented them choosing ambush positions based on the angle of coral structures, current direction, and prey escape routes. They appear to calculate where their prey will move, not just where it is. This behavior mirrors the concept of predictive modeling, an advanced form of decision-making where past outcomes inform future actions. Each failed hunt becomes data, each successful strike reinforcement. Over time, the grouper refines its geometry of attack, turning the labyrinthine reef into a personal hunting map. At cleaning stations, those neutral zones of the reef where predation is suspended and cleaner fish remove parasites from their larger clients, the grouper's social intelligence appears again. Here, dozens of species converge in a delicate ritual of trust. Cleaner wrasses flit from body to body, nibbling at parasites while predators hold still, mouths open, fins extended. The grouper waits its turn patiently, hovering at a specific location where the wrasses recognize it as a regular. These fish are capable of remembering individual clients, and groupers in turn seem to remember particular cleaning stations. They visit the same ones repeatedly, often at consistent times of day. Such time-place associations, returning to precise sites on predictable schedules, require internal biological clocks and long-term spatial memory. What's remarkable is that this punctuality benefits not only the grouper, but the cleaners themselves. Knowing when large clients will arrive allows the wrasses to pace their workload and avoid competition. This symbiosis between predator and parasite cleaner becomes another form of mutual understanding, maintained not by instinct alone, but by learned timing. Within the daily rhythm of the reef, even acts of hygiene become lessons in communication. Groupers also exhibit remarkable patience, a predator's virtue that hints at cognitive depth. During cooperative hunts, a grouper may wait for minutes, hovering motionless near an eel's hunting crevice, responding only when movement stirs within. If the eel fails to flush prey, the grouper may try again with another partner or shift to a different coral structure. The decision is not random, it reflects situational assessment. A grouper's ability to alternate between hunting methods, solo suction feeding, cooperative ambush, or active pursuit shows behavioral flexibility comparable to that seen in intelligent birds and mammals. Even the act of recruitment demonstrates a form of empathy, or at least perspective-taking. The grouper appears to understand that the eel perceives the world differently, that what is hidden to one is accessible to the other. This is an advanced cognitive trait known as complementary role understanding. It allows both species to exploit each other's strengths without competition. In this way, the grouper is not merely a predator, it is a strategist, using the ecosystem itself as a network of potential collaborators. The coral reef, complex and crowded, rewards such intelligence. Each coral head and sandy passage is both shelter and trap, its geometry dictating life and death. Groupers, with their spatial awareness and cooperative adaptability, occupy a niche where brute strength alone is insufficient. Their massive jaws are balanced by brains wired for pattern recognition and recall. A grouper that remembers which coral crevice hides which prey species gains a tangible advantage. It hunts with context, not instinct. Observations have also revealed that groupers can distinguish between different types of prey concealment. They appear to recognize when a fish has buried itself in sand versus hiding in coral, adapting their approach accordingly. In sandy conditions, they may summon not morays but other partners, such as octopuses, whose probing arms can dig prey from the substrate. These flexible alliances suggest not fixed instinct but improvisation. The grouper is effectively recruiting the right specialist for the right task, an ecological analog of human problem-solving. Within this behavior lies a deeper evolutionary insight. Cooperation among predators is rare, especially across species. It requires communication that transcends vocalization or display, communication built on shared goals. The grouper and its partners demonstrate how intelligence can evolve not from social bonding alone, but from environmental necessity. The coral reef, crowded and resource-limited, pressures its inhabitants to innovate or perish. In that pressure, cognition emerges as survival strategy. At dusk, the reef transforms again. The water cools slightly, and the shimmer of daylight gives way to the blue gloom of evening. The grouper patrols its range, the edges of coral glowing faintly under fading light. It pauses at a familiar outcrop, one it has hunted many times before. With a subtle flick of its fins, it signals, and from a nearby crevice, a moray eel begins to stir. The two predators move together through the labyrinth of coral, partners in an old, silent understanding. They hunt not with sound, but with shared awareness, a choreography born from memory and practice. Every twist in the reef, every shadowed passage, is a line in their shared playbook. When the eel dives into a hole, the grouper waits by the exit, anticipating motion. Seconds later, a flash of silver shoots outward, and the grouper's jaws open in an instant. The hunt ends before it begins. In the grand hierarchy of ocean life, intelligence often hides in unexpected places, not in brains built for social drama or language, but in minds tuned to pattern, cooperation, and adaptation. The grouper, broad and unassuming, stands among the reef's most sophisticated tacticians. It reads the environment like a strategist reads terrain, turning coral into geometry and neighbors into allies. And when the hunt is done, it glides back into shadow, vanishing into the reef's maze with the confidence of a creature that knows its domain intimately. To watch it move is to glimpse cognition written not in tools or words, but in instinct sharpened by memory. The quiet intelligence of a recruiter in a world where survival depends not only on strength, but on the art of partnership. The wind moves across the Southern Ocean like a living force, an endless sweep of cold air and salt that never truly rests. Icebergs drift through the grey, their surfaces etched by time and current, and the water beneath them churns with invisible lines of temperature and nutrients that define where life will bloom. Amid this vast, merciless expanse, a black and white shape cuts through the water with the precision of a torpedo. A penguin, small in a world of giants, glides through the sub-zero surf, carving invisible paths between sea and colony. It moves not randomly but with purpose, as if the frozen ocean itself were a familiar map. Every dive, every ascent, every turn through this underwater labyrinth is guided by memory, a three-dimensional navigation learned not from maps or stars, but from generations of experience written in instinct, motion, and shared observation. To understand the penguin's intelligence, one must leave the ice and follow it beneath the surface into a world of blue darkness where pressure builds and sound travels like a drumbeat through water. Here, penguins are not clumsy creatures waddling on land, they are athletes of precision. Their flippers, stiffened by bone and edged by strong tendons, act as hydrofoils, turning each stroke into thrust. They dive hundreds of meters, pursuing schools of krill or silverfish that flicker like galaxies suspended in the deep. Yet this movement is not simply chase, it is navigation. Penguins dive not where food is, but where food will be, guided by memory of currents, light angles, and thermal layers invisible to any human eye. At sea, the penguin's world exists in motion, a three-dimensional treadmill of shifting reference points. Unlike terrestrial animals that navigate by landmarks, penguins must rely on cues that move and change. Temperature gradients, salinity differences, and the faint geomagnetic fields that sweep across the polar regions. Studies have shown that penguins returning from long foraging trips, sometimes hundreds of kilometers from their nesting sites, follow routes almost identical to those used days or weeks earlier. This fidelity is remarkable in an environment that never looks the same twice. Sea ice advances and retreats, prey migrations shift, and storms erase all physical traces. Yet the penguin remembers not objects but relationships, how distance, direction, and ocean texture combine into patterns. This spatial memory is stored and refined through repeated experience, allowing individuals to locate productive feeding grounds with uncanny precision. These feeding zones, known as oceanic fronts, are the arteries of the Southern Ocean. Here, cold nutrient-rich water from the deep meets warmer surface layers, igniting explosions of plankton that attract krill, squid, and small fish. Penguins learn to recognize these regions by subtle environmental cues, changes in wave motion, the smell of plankton carried on the wind, or even the presence of other species like seals and petrels. Young penguins, newly fledged from the colony, begin with trial and error. They explore widely, following instinctual drives that pull them toward areas of higher productivity. Many do not survive their first months at sea, but those that do return with knowledge, a learned understanding of where the ocean gives life most freely. Their navigation is not solitary. Back at the colony, where tens of thousands gather on icy shores, penguins share information in ways that blur the line between instinct and teaching. When adults return from the sea, they are met by calls and jostles, surrounded by hungry chicks and watchful neighbors. Within this chaos, subtle patterns emerge. Penguins that have recently returned from productive feeding areas often leave the colony again with others in tow, leading them along similar routes. Observers have documented coordinated departures and synchronized swimming in early foraging stages, suggesting that penguins may use social learning to refine navigation. This communal exchange, passing on mental maps through behavior rather than vocal instruction, represents one of the most effective survival strategies in an ocean defined by unpredictability. Underwater, these learned routes translate into efficiency. A young penguin's early dives are shallow and erratic, often breaking the surface after a few dozen meters, its body poorly streamlined and its lungs unpracticed at pressure adaptation. But with time, experience reshapes physiology. Mature penguins dive in elegant, energy-efficient arcs, reaching depths exceeding 200 meters, adjusting their buoyancy dynamically by altering air volume in their plumage and lungs. They learn to use water resistance and gravity to their advantage, gliding downward on descent and letting residual air in feathers lift them gently toward the surface on return. This is not simple instinct. It is performance shaped by feedback, trial, and error, proof that even in the coldest waters, cognition finds a way to optimize survival. Yet the penguin's education does not end with mastery of movement. In a world of competition, it also learns deception. Food at sea is not infinite, and every meal stolen from one creature is denied to another. Penguins have been observed shadowing seals as they hunt, taking advantage of fish flushed from hiding by the larger predators. In some regions, they follow leopard seals closely, darting in to snatch stray fish that escape the seal's initial strike. The danger is obvious. The seal is capable of killing the penguin, but experience teaches the bird when to close distance and when to retreat. A similar cunning appears at the colony's edge, where skuas, large predatory seabirds, attack chicks or steal food regurgitated by returning adults. Penguins have learned to counter this through distraction, forming small defensive clusters or feigning vulnerability to lure skuas away from nests. These acts of strategy, repeated and refined, demonstrate that penguins are not passive participants in evolution's script. They are active players, learning from risk and improvising in real time. The complexity of penguin behavior extends to communication. Each species possesses distinct vocal patterns, but within colonies, individuals recognize mates and chicks through unique vocal signatures. These acoustic identities, stored and recalled over months-long separations at sea, are the backbone of their social cohesion. But beyond the familiar calls of reunion lies another layer of intelligence: timing. Penguins adjust their return to the colony according to the feeding schedules of their chicks and the changing conditions of the sea ice. They exhibit what biologists term temporal memory, an awareness of cyclic events linked to both internal biological rhythms and external environmental cues. By synchronizing their movements with ocean productivity, they maximize feeding success while minimizing wasted effort. One of the most striking demonstrations of penguin learning occurs in their dive profiles. With age, penguins modify not just how deep they dive, but how they structure their dives over time. Juveniles tend to perform uniform, shallow dives, while adults develop wiggle dives, a pattern of ascending and descending movements within a single dive cycle. This allows them to sample multiple depth layers where prey may concentrate, effectively turning a single dive into a vertical survey. The transition from simple to complex dive patterns mirrors the learning process itself. Experience expands awareness, turning guesswork into strategy. Navigation also demands physiological mastery. When a penguin dives, it must balance oxygen conservation against metabolic output. Its heart rate drops dramatically, sometimes to fewer than 10 beats per minute, to conserve oxygen. Blood flow is prioritized to vital organs, while muscles rely on stored oxygen bound to myoglobin, a specialized protein that gives them their dark color. This adaptation allows extended foraging beneath ice sheets, where surface access may be temporarily blocked. The coordination of movement, respiration, and spatial memory forms a biological symphony of survival, one that reveals the deep integration of body and mind. Above the surface, the penguin's navigation continues in a different dimension. The Antarctic landscape is a shifting maze of ice ridges and pressure cracks, where storms can erase landmarks within hours. Returning from the sea, penguins must find their exact colony, and within it, their specific nesting site, often across kilometers of featureless snow. They use a combination of visual recognition, smell, and magnetic orientation to achieve this. Experiments show that penguins can detect Earth's magnetic inclination and polarity, using it as a compass when visual cues vanish. On clear days, they also use the sun's position and the pattern of polarized light across the sky to maintain direction. The result is near-perfect homing ability, refined through years of repetition. Their navigation through this frozen labyrinth is not without error, and the cost of mistakes can be fatal. A penguin disoriented by blizzard conditions may wander off course and perish of exhaustion. But the survivors, those that learn to read subtle wind direction, snow hardness, and distant colony calls, carry those lessons forward. In this way, experience becomes evolution in motion, written across generations. When viewed from above, a colony appears chaotic, a mass of moving bodies and noise. But beneath the surface of that apparent disorder lies order built on learning and communication. Penguins do not simply endure the Antarctic, they master it, using intelligence shaped by necessity and refined by cooperation. They navigate not by instinct alone, but through memory, adaptation, and shared information, a kind of distributed cognition spread across thousands of individuals. As the light fades and the horizon glows with the soft hues of an Antarctic dusk, penguins return from the sea, bellies full, feathers beaded with salt and ice. They follow the same unseen routes carved into their minds, paths that cross a living ocean and return to a single point on the shore. To the eye, it looks miraculous that a bird can find its way through a frozen desert and an endless sea without maps or markers. But to the penguin, it is simply learned truth, knowledge earned stroke by stroke, dive by dive, year after year. In the end, the penguin's genius is not in invention or complexity, but in constancy. It learns from the sea's shifting face, from the ice's retreat and return, from the dangers that claim the careless and reward the patient. It lives by adaptation, by experience, by an ever-evolving map of its frozen world, a navigator of ice and current whose compass is memory itself. The mangrove forest at dawn is a world of half-light and motion. Shafts of sunlight pierce through tangled roots, flickering across the water's surface as the tide creeps inward. Beneath the stillness, shadows drift with silent precision, pale, translucent shapes that seem more apparition than animal. The box jellyfish, nearly invisible in the dappled shallows, moves with an economy of purpose that belies its simple anatomy. It pulses forward through narrow channels, navigating the maze of mangrove roots with a precision that would challenge even a fish. There is no brain guiding this movement, no central command, no organ for thought or planning. Yet somehow it learns. To call the box jellyfish intelligent is to stretch the definition of the word, but only slightly. Within its gelatinous bell, clustered at each corner, lie small sensory structures called ropalia, 4 of them in total. Each ropalium holds 6 eyes of varying complexity, giving the jellyfish a total of 24. 2 of these eyes, known as camera-type eyes, possess lenses, corneas, and retinas remarkably similar to those found in vertebrates. They focus, track movement, and form real images. The others detect light intensity and horizon lines, gauging the direction of sunlight even when the animal is submerged in murky water. Together, these eyes feed data into a decentralized network of neurons that encircles the jellyfish's body like an information ring. It is not a brain, but it functions as one, a distributed intelligence woven into the tissue of the animal itself. Here in the shallows of northern Australia, this primitive mind faces one of the most intricate navigational challenges in the marine world. The mangrove estuaries are dense and shifting. Roots twist upward like wooden spears, water levels rise and fall with the tides, and visibility fluctuates by the minute. Yet box jellyfish thread their way through these corridors daily to hunt small crustaceans and fish larvae. They must avoid grounding themselves on roots or being trapped in dead-end pools when the tide retreats. In laboratory studies, researchers have recreated this environment, a maze of vertical poles mimicking mangrove roots, and watched as box jellyfish learned to avoid collisions. Within minutes, they adjusted their pulsing rhythm and steering angles to pass cleanly through gaps they had previously struck. This rapid associative learning, achieved without a central nervous system, challenges nearly every assumption about what a simple animal can do. The mechanism behind this learning lies in the flexibility of the jellyfish's nerve net. Unlike higher animals, whose neurons are clustered into specialized regions, the box jellyfish's neural network is spread throughout its bell and tentacles. Every contraction pulse is modulated by feedback from sensory input. When its visual sensors detect an approaching obstacle, the local nerve circuits increase the frequency of contraction on one side of the bell, steering the animal away. If a collision occurs, the network updates its response. The strength and timing of pulses are altered on subsequent movements, reducing the likelihood of repeating the mistake. This is adaptive learning in its most elemental form. No memory stored in a central organ, but in distributed patterns of synaptic weight changes across its body. What makes this adaptation more astonishing is that the jellyfish's eyes are not merely passive detectors, they create context. The box jellyfish distinguishes between light filtered through open water and that refracted through dense roots or sediment. When navigating under bright sunlight, it increases its pulse strength, moving faster and straighter. In dim conditions, or when the light becomes fragmented, it slows down and begins to turn cautiously. These behavioral shifts demonstrate a form of conditional response, an awareness of environment that is both visual and behavioral. In essence, the jellyfish perceives the difference between open and obstructed space, adjusting its movement accordingly. This sensitivity is not merely for navigation, but survival. The mangrove zone is a dangerous place for gelatinous bodies. Small fish dart between roots, some feeding on jellyfish tentacles. The ebbing tide can strand them in shallow pools where heat or salinity spikes prove lethal. Yet, despite these threats, box jellyfish thrive here. Their bell pulses propel them at speeds exceeding 6 feet per second, making them among the fastest swimmers of all jellyfish species. Their agility allows them to outmaneuver small predators and actively hunt rather than drift. They use their long, venomous tentacles as nets, positioning themselves strategically in tidal channels where the current funnels prey. Each tentacle is armed with thousands of nematocysts, microscopic harpoons that fire on contact, delivering venom potent enough to stop a human heart in minutes. The venom's power speaks to evolutionary efficiency rather than malice. It immobilizes prey almost instantly, preventing escape or injury to the fragile tentacles. Each stinging cell fires only once, then is replaced, meaning every strike carries a cost. The jellyfish's precision in hunting, its ability to control when and where tentacles extend, reduces wasted effort. Observations suggest that the box jellyfish can modulate its tentacle spread based on environmental cues. Wider arrays in open water, tighter and more controlled when maneuvering around obstacles. This level of control, paired with rapid sensory feedback, implies a form of decision-making distributed through the body's network, a system that balances energy conservation with risk and reward. Vision plays another crucial role in feeding. Box jellyfish do not rely solely on passive drift to encounter prey. They actively position themselves in areas of contrast and movement. Their camera-type eyes are directed outward and downward, giving them a panoramic view of both the water ahead and the substrate below. When the light flickers as small fish or shrimp pass through, the jellyfish increases pulse frequency, steering toward the disturbance. Unlike most jellyfish that rely on chance encounters, Box jellyfish actively target prey using sight, a hunting method closer in spirit to that of vertebrate predators. Equally striking is how they integrate short-term learning into their hunting strategy. In experiments where prey availability changed between zones of light and dark, box jellyfish quickly learned to associate brightness with higher prey density, congregating in illuminated areas. When the conditions were reversed, they adapted within minutes. Such rapid behavioral adjustment, driven by visual association, is rare among animals lacking a brain. It demonstrates that the nerve net can update internal models of reward and environment, a foundation for learning that predates centralized cognition by hundreds of millions of years. From an evolutionary standpoint, the box jellyfish's distributed intelligence offers a glimpse into how the first nervous systems may have functioned. Rather than emerging fully centralized, early neural networks likely began as decentralized webs of sensory motor feedback, bodies that thought with their entire surface. In the box jellyfish, this ancestral architecture persists, honed by selection into a remarkably capable form of cognition. It shows that learning and adaptation do not require a brain, only a system capable of perceiving change and modifying response. The implications stretch beyond biology. Neuroscientists study box jellyfish not only to understand marine life, but to explore fundamental principles of learning and control. Their distributed neural networks inspire research in robotics and artificial intelligence, where decentralized processing enables machines to adapt to complex environments without a central processor. The box jellyfish, a creature often dismissed as primitive, thus stands as a model for resilience and efficiency, a living algorithm of motion and awareness. In the ecosystem, their role extends beyond predation. By consuming large numbers of small crustaceans, they help regulate plankton populations, influencing nutrient cycling and energy flow in coastal systems. Their presence also controls the abundance of other gelatinous competitors, maintaining ecological balance. Yet their population dynamics are finely tuned to environmental shifts. Warmer waters and nutrient enrichment from coastal runoff have, in recent decades, led to more frequent jellyfish blooms, including box species. These surges disrupt fisheries and pose threats to swimmers, reminding humans that even the simplest organisms can shape entire ecosystems when conditions change in their favor. As daylight deepens, the mangrove channels fill with particles of silt, turning the water into a shifting mirror. The box jellyfish glides through with measured grace, each pulse propelling it forward in perfect rhythm. Its eyes scan the luminous haze, detecting silhouettes of roots and fish, constantly adjusting course. There is no brain behind these movements, no command hierarchy, only the seamless conversation of sensors and muscles, perception and action. In that dialogue, learning occurs, experience accumulates, and behavior refines. When night falls, bioluminescent plankton begin to glow in the shallows, scattering pinpricks of light that drift like stars beneath the surface. The jellyfish moves among them, its bell catching the faint shimmer, each pulse sending ripples of light cascading through the water. To human eyes, it appears ghost-like, mindless, eternal. But within that gelatinous form is one of evolution's earliest minds, a system so minimal and yet so efficient that it redefines what it means to think. The box jellyfish does not ponder, but it perceives. It does not reason, but it learns. Its eyes without a brain remind us that intelligence is not a privilege of complexity. It is a property of life itself, emerging wherever perception meets adaptation. In the silent maze of the mangroves, that truth drifts, translucent and patient, pulsing with the rhythm of thought older than the brain. The Caribbean dusk begins with color and ends in chemistry. As the sun fades beyond the shallows, the water cools, and the spiny lobsters emerge from their rocky dens like a slow-moving tide of armor and antenna. Their long spines catch the dim light in flashes of bronze and pearl, and their eyes, compound spheres adapted for low light, gleam like polished glass. The reef, quiet by day, hums to life in chemical language. Every passing current carries messages of territory, hunger, and fear. For the spiny lobster, the night is not just a hunt for food, it is a navigation through an invisible world of scent, a map written in molecules. Unlike their clawed relatives of colder waters, spiny lobsters rely less on brute force and more on social organization and communication. Their power lies in coordination, each individual a sensory node in a vast decentralized network. Their long, feathered antennules flick constantly through the water, sampling thousands of chemical particles per second. To a lobster, this sensory input forms a living map. Trails of odor that mark where others have passed, traces of predators that linger in the current, even the faint molecular residue of home. What appears to human divers as a featureless seafloor is, for the lobster, a scented highway system connecting dens, feeding grounds, and migration routes that stretch for kilometers. Nowhere is this more visible than during the great annual migration, a phenomenon that transforms these solitary crustaceans into disciplined travelers. As the seasons shift and cooling waters signal the approach of winter, spiny lobsters gather in astonishing numbers, leaving the safety of reefs to march across open sand plains toward deeper, warmer waters. This mass movement, sometimes stretching hundreds strong, unfolds with near-military precision. Lobsters align in single-file columns, each individual maintaining physical contact with the one ahead through its antennae. The line undulates across the seabed like a living train, its rhythm dictated by touch and chemical cues. This behavior, extraordinary for an invertebrate, demonstrates both memory and collective intelligence. Each route is not rediscovered anew but retraced, handed down through generations via environmental imprinting and social learning. Young lobsters follow the paths established by older ones, memorizing the combination of olfactory signatures and hydrodynamic features that define the corridor. These scented highways are reinforced year after year by the passage of many feet and the release of specific pheromones, which mark the trail like beacons in the water. Even after storms erase physical landmarks, lobsters can relocate their migration paths, guided by these persistent chemical cues and the faint geomagnetic variations they have learned to associate with safe passage. The logistics of these journeys reveal an organism finely tuned to collective decision-making. Lobsters use chemical signals not only to stay together, but to coordinate timing. When environmental factors, temperature, salinity, or day length, shift beyond certain thresholds, individuals begin secreting aggregation pheromones from specialized glands near their antennules. The scent triggers others nearby to join, snowballing into a cascading response across the population. In this way, migration begins not from a central leader, but from a distributed agreement, an emergent consensus arising from countless sensory interactions. The result is one of the most synchronized and self-organized movements in marine life, accomplished without hierarchy or vocal communication. But scent serves more than navigation. It governs their social order. Spiny lobsters are highly territorial creatures, yet they share dens with surprising tolerance, so long as each resident abides by the chemical rules of hierarchy. When two lobsters encounter one another, they exchange more than physical threats. They release chemical signals carried in the water and more notably in jets of urine expelled from nozzles near the base of their antennae. This urine signaling is not a primitive accident, but a deliberate form of communication. The fluid contains compounds that convey identity, reproductive status, and dominance. During confrontations, a dominant lobster releases a stronger and more concentrated chemical profile, effectively announcing its superiority. The subordinate, upon detecting this scent, typically retreats without escalating the conflict. This exchange of information prevents injury in a species equipped with formidable weaponry. The spiny lobster's antennae can deliver forceful strikes capable of deterring octopuses and moray eels. Yet among themselves, physical combat is rare. The chemical language ensures that dominance is maintained efficiently and with minimal risk. Experiments have shown that when lobsters are deprived of their ability to sense these urine-borne cues, fights become more frequent and more violent, confirming that scent, not strength, maintains order. The same sensitivity underpins their remarkable homing ability. Lobsters rarely settle randomly. When displaced from their dens, they can navigate back with astonishing accuracy, even across unfamiliar terrain. The secret lies in the interplay between odor plumes and magnetic orientation. Each den has a distinct chemical signature, a mixture of microbial, algal, and waste-derived compounds that create a unique olfactory fingerprint. Lobsters memorize this scent profile over time, linking it with subtle geomagnetic coordinates stored in their nervous system. When far from home, they detect gradients of these familiar odors carried on currents, using them to triangulate their way back. It is a chemical form of GPS, achieved with nothing more than antennae, nerves, and a brain the size of a grain of rice. These abilities extend into community living. Within a shared den, lobsters maintain social structure through scent-based recognition. Individuals identify familiar conspecifics and adjust behavior accordingly, showing less aggression toward known neighbors. This dear neighbor effect mirrors patterns seen in territorial birds and mammals, proof that complex social strategies are not limited to warm-blooded species. Chemical familiarity promotes stability within the group, while the combination of physical contact and shared odor maintains cohesion during risky migrations. When they march in their long, sinuous chains, each lobster recognizes its companions by smell as much as by touch. At night, when the migration halts, the columns disband temporarily. Individuals fan out to forage on small mollusks, decaying vegetation, and carrion. During these excursions, their antennae continue to flick rhythmically, sampling the chemical backdrop of the environment. Every pulse of the water brings updates. Who has been here recently? What predators passed through? Whether other lobsters have found nearby shelters? In effect, they read the reef's chemical newspaper, keeping track of its invisible stories. When the group reforms before dawn, these accumulated scent impressions inform the next stage of the journey, subtly influencing which direction the chain turns or where it pauses to rest. The complexity of these behaviors reveals a mind that, while simple in structure, operates on principles of distributed intelligence. The spiny lobster's nervous system lacks the centralized processing of vertebrates. Instead, its sensory inputs are processed locally and integrated through feedback loops. Each individual acts as both decision-maker and sensor, and through countless small adjustments, collective order emerges. In modern biological theory, such systems are described as swarm intelligence, a phenomenon where the group achieves sophistication beyond the sum of its parts. The spiny lobster's migration is a living demonstration of this concept, realized long before humans coined the term. Yet their reliance on scent and sociality also exposes them to environmental vulnerability. Chemical communication depends on clean, predictable water chemistry. Pollution, sedimentation, and warming seas interfere with these signals, breaking the links that connect individuals and their migratory traditions. In areas where chemical gradients have been disrupted by runoff or algal blooms, lobster migrations falter. The animals become disoriented, settling in unsuitable habitats where food is scarce and predators abound. These failures remind us how tightly the species' survival is tied to the stability of its sensory world. To lose the ocean's chemical balance is, for the lobster, to lose its language, its map, and its society all at once. Despite these challenges, the species endures, adaptable, social, and remarkably perceptive. Beneath the surface, an evolutionary lesson unfolds. Intelligence is not the sole domain of creatures with large brains or expressive eyes. It can exist in the whisper of molecules, in the rhythm of antennae, in the coordination of hundreds of individuals marching across the seafloor guided only by scent. As dawn returns to the Caribbean, the columns of spiny lobsters press on, their antennae sweeping forward like the sensors of a machine that never stops analyzing. The sand beneath them bears faint tracks, soon erased by the tide. To them, the landscape is not empty, but alive with chemical echoes of those who came before. They march along highways no human can see, guided by a map that exists only in the language of smell, an ancient script written in seawater and memory. And so they move, silent, collective, and unerring, following the invisible roads that link one season to the next, one generation to another. In their world of scent and current, navigation is not a matter of sight or sound, but of memory preserved in molecules. For the spiny lobster, the ocean is not vast and featureless. It is home, written one molecule at a time. Night settles over the reef like a living shadow. As the last shafts of sunlight fade, the coral fortress transforms. Daytime fish retreat into crevices, their bright scales replaced by the muted colors of hunters rising from the gloom. The water grows cooler, the current more deliberate, and somewhere within the labyrinth of coral stone and sponge tunnels, a slow shape stirs. From a narrow slit in the rock, a head emerges, serpentine, sleek and ancient in form. The moray eel slides forward, its jaw rhythmically opening and closing as it samples the water. Its greenish skin shimmers faintly under the faint scatter of moonlight, and its eyes adjust to the dim world ahead. This is the hour of precision, the time when the moray transforms from a hidden shadow into a strategist. Every night, this eel moves through its reef as if tracing invisible lines. To an outsider, its navigation seems effortless, but beneath that fluid grace lies something extraordinary: memory. The moray eel is not a wanderer, but a cartographer of stone. Within its elongated skull and small but efficient brain, it stores spatial information of its home range with astonishing accuracy. It knows every crevice, every corridor, every side channel of its maze-like territory. It knows which tunnels connect, which dead end, which offer two exits for escape. These dens are not random shelters. They are rehearsed stage sets for survival, rehearsed through repetition, until every angle of attack and retreat is muscle memory. Marine biologists studying reef predators often describe the moray's home as a multi-entrance fortress, a structure optimized for both ambush and escape. Inside, the eel moves with the confidence of familiarity. Its long, flexible body snakes through the maze, brushing along walls whose texture it recognizes like a fingerprint. Its skin, coated in a layer of protective mucus rather than scales, allows it to slip through sharp coral with minimal abrasion. This adaptation is more than armor. It is a design choice refined by millions of years of evolution for life inside stone. Where other predators rely on speed in open water, the moray relies on geometry and memory. In the reef's darkness, sight alone is of little use. Instead, the eel depends on smell and the lateral line system, a network of pressure-sensitive cells along its flanks that detects vibrations in the water. Through these sensors, it perceives the shape of motion itself, the flutter of a sleeping parrotfish's fins, the tremor of a crab shifting under rubble, the approach of a rival eel. Each ripple becomes part of the eel's mental map, overlaid atop the physical architecture of the reef. In time, the two maps merge, structure and motion intertwined. The eel no longer simply hides within coral. It thinks through it, predicting how prey will move based on experience. When hunting begins, the moray does not chase. It waits. Its strategy is built around the physics of confinement. Prey that strays near its entrance sees only darkness, not realizing that the narrow passage conceals a coiled predator. In one explosive motion, the eel lunges forward, its mouth opening wide to reveal a second set of jaws buried deep within its throat. These are the pharyngeal jaws, one of nature's strangest inventions. When the moray bites, these inner jaws shoot forward, gripping prey and pulling it backward into the esophagus. Unlike most fish that use suction feeding, morays rely on this dual jaw mechanism, allowing them to feed effectively within tight spaces where suction would fail. But the act of striking is not random. Observations show that morays choose ambush angles based on prior success. They remember which exits prey tend to use, which direction currents favor, and which holes produce the best hunting yield. Over days or weeks, this pattern refines into learned precision. They alter their body posture and weighting depth to account for specific prey species. A shrimp-hunting moray, for instance, may hold closer to the sediment line, while one specializing in small reef fish may wait suspended mid-den. This adaptation demonstrates a rudimentary form of behavioral optimization, a predator adjusting its methods through experience rather than pure instinct. The eel's memory extends beyond individual hunts. Studies using tagged individuals show that morays repeatedly return to the same network of dens across months, following near-identical routes during nocturnal foraging. This spatial fidelity suggests not just familiarity, but strategic reinforcement. By reusing known paths, the eel reduces exposure to open water predators such as reef sharks or groupers. It also exploits the rhythmic habits of prey that frequent predictable shelter zones. In this sense, the moray's reef is not merely habitat. It is a living algorithm of probability, constantly updated through the repetition of survival. In the dim silence of the night reef, the eel's senses are amplified. Chemical cues disperse slowly in the still water, and each flick of its tongue-like nostrils, the tubular nares, draws in micro traces of life. These odor molecules travel to a sophisticated olfactory center, enabling the eel to distinguish between prey species and even individual scent trails. This chemical acuity allows it to detect injured fish or molting crustaceans long before visual confirmation. The combination of smell, vibration, and memory creates a triangulation system, one that turns the reef into a dynamic hunting grid. As the eel patrols, it also displays another remarkable behavior: cooperative hunting. In some reefs, morays form temporary partnerships with groupers. The grouper, unable to flush prey from crevices, signals to the eel with a distinctive head shake or body posture. Responding to this invitation, the moray enters the crevice system, driving prey into open water where the grouper can strike. In return, the moray gains access to prey that would otherwise remain unreachable. This alliance, observed across multiple species and repeated consistently, indicates recognition and associative memory between individuals, one predator remembering another's role. In evolutionary terms, this cooperation hints at an intelligence level rarely attributed to fish. Back in its den after feeding, the moray repositions itself within the coral architecture. It does not rest randomly. The eel often aligns its head toward the most trafficked entrance, positioning its body in an S shape that allows instant acceleration in either direction. This habit suggests spatial awareness of risk and readiness, a behavioral pattern shaped by repetition and memory. Even in rest, it rehearses escape. Predators like sharks or barracudas that attempt to dislodge it often fail, as the eel disappears through a side passage known only to itself. The reef's twisting corridors become extensions of its own body, muscle and stone in perfect synchronization. What makes the moray eel's memory even more remarkable is its adaptability. When storms or coral collapses alter the structure of its territory, the eel does not lose its orientation. It explores, updates, and rebuilds its mental map over time. In laboratory maze experiments, morays learn to navigate artificial tunnels with multiple exits, demonstrating retention for weeks after. They remembered which paths led to food rewards, even when visual landmarks were removed. Such resilience in spatial learning underscores their ability to adapt to dynamic ecosystems where habitat structure is constantly shifting. Yet this intelligence is not abstract, it is survival embodied. For a moray, every inch of reef is potential refuge or trap. The success of its ambushes depends on intimate familiarity with its terrain, and that familiarity is earned through iteration. Its life is one of repetition and refinement, a daily reenactment of memory turned instinct. Evolution has shaped its mind to value the local over the distant, the familiar over the new. It does not roam widely like pelagic hunters. It masters what is near until mastery becomes invisibility. As dawn approaches, the reef begins to glow again. Colors return to coral, and the first rays of sunlight pierce the water column. The moray withdraws into its labyrinth, vanishing into the geometry it knows best. Its skin blends seamlessly with the encrusted limestone, and its rhythmic breathing slows to a whisper. The reef reclaims its calm. Small fish dart cautiously past the entrance, unaware that behind that motionless facade lies a creature that has memorized every contour of their world. In the moray eel's existence, intelligence is not displayed through curiosity or exploration, but through spatial certainty. It survives by remembering the unchanging truths of its domain: where to hide, where to strike, where to vanish. Its maze is both home and mind, an external memory carved in coral and rehearsed night after night until the reef itself becomes an extension of thought. And as the currents shift and the coral grows, the eel adjusts in kind, patiently learning, forgetting, relearning, its life a continuous conversation between memory and motion. For the moray eel, thinking is not a matter of reflection, but of repetition. Its wisdom lies in the reef's narrow corridors, where every movement is practiced, every exit memorized, and every hunt an echo of those that came before.